Okay, cool. Let's get started. Thanks all for coming. Thanks all for the very nice introduction. I'm going to tell you about evaluation today in the context of training sets, how we evaluate training sets. But first of all, let me say I'm just super excited that we have an entire workshop on evaluation, because this is, I think, just a very, very important topic in AI. I think has played a really key role in the amazing progress we've seen over the past 10 to 20 years in AI. So like these benchmarks that everyone is familiar with, like here's a picture, I think this is MS COCO, the object detection benchmark. This is really prototypical for a lot of research here at CDPR and other AI conferences. And these benchmarks are really key in organizing community and allowing us to really measure progress in a consistent way to figure out what works well and what doesn't. And keeping the microphone doesn't work well, but that's okay. And I just speak louder and people are hopefully okay. Is it okay in the back? Okay, the moment we have a thumbs up in the back. I just move out, and then if it goes bad, then just interrupt. Okay, cool. So yeah, benchmarks are great for measuring progress. And a lot of discoveries in AI were aided by benchmarks. And just to give a couple examples here, I actually like it more if I can move around. So okay, it's okay. And then let's give it a try. What's really bad? Is it back in the back? Can people hear me? No, it's okay. At least one person in the back can hear me. Okay, so examples of discoveries enabled by benchmarks. I think the prototypical here one is MNIST. So like the fact that ConvNets work really well was first established among other places on this MNIST datasets. Then we had CIFAR-10, training on GPUs as a thing. Alex Krzyzewski's first GPU-based content implementations, they happen on CIFAR-10. And then Multimodal obviously is in large part responsible for deep learning resurgence, discoveries like ResNets, residual connections, transfer. And in all of these benchmarks really clarified that something big was happening, because we saw a large increase in image adapters. Okay, so this is all great. We've learned a lot from this. So like the paradigm here typically is data set is fixed, and then people innovate by improving on the model side, new model architectures, new training algorithms, and so on. And I think we have learned a lot from it. As I said, amazing breakthroughs. But as a result of that, comparatively much fewer papers experiment with improving the training. And I think this is the one shortcoming of this like current benchmark paradigm. At a high level, if we think about AI, it consists of two parts, right? Compute and data. And so like on the compute side, as we just said, we have seen a lot of nice discoveries enabled by these benchmarks, better optimization algorithms, better model architecture, better loss functions, and more. Like hundreds of thousands of papers every year at conferences like CDPR, Europe, and so on that make it very consistent. And compared to that, on the data side, there's still much less work that systematically studies how we build high-quality training sets. And I think this is currently sort of a bit of a blind spot in the AI research ecosystem, and something we need to address. And to be fair, people are already starting to address this. Like Europe now has a data sets track this year in the third iteration. That's super exciting to see how quickly this is growing. And also here, CDPR earlier today, for instance, I was at a workshop on synthetic data. That was obviously also focusing on data side. And just to like underline again, like how important these data sets are, you really could not do state-of-the-art AI as we're doing right now without large training sets. Like for instance, one example here is like the GPT sequence of models. If you roughly look at how large these training sets are, from GPT-1, trained on maybe around 3 billion tokens, to GPT-4, maybe rumored to be trained on 3 trillion tokens. I mean, we don't know exactly anymore. For GPT-3, it's still in paper. Anyway, these data sets have grown a lot over the span of 5 years. And then also in computer vision, ImageNet was still sort of like, by current standards, easy to manage 1 billion images, and then Lion 5B, 13 years later, became 5,000 times larger, 5 billion images. Cool. And so like today, I want to tell you a bit about work we've done on benchmarks, on evaluation for training sets. But in order to get there, we first need to go a little bit on a journey through 3 years of data sets for multimodal learning. Because that is going to build the context for the benchmark we don't know. And when I say multimodal learning, just to make sure we are on the same page here, I specifically have 2 problems. And one is image understanding in the form of image classification. So like image goes in, text label comes out, and then the opposite direction obviously is generating images. Text description goes in, image goes out. So these are going to be the leading sort of like multimodal learning problems we're going to look at. And in both of these domains, January 5, 2021 was a very important date because on that day, OpenAI put out two really nice papers, the CLIP paper for image understanding and a DALI paper for image generation. And they really moved the field forward by showing how much better these methods get if you scale them up. And specifically on the CLIP side, one thing that I really like, because I've worked a lot on reliable generalization, was that these CLIP models are a lot better in terms of reliable generalization. Like we did much better than prior work on out-of-distribution test sets. And then the DALI models, obviously, were the first ones to show how far you can go with text-guided image generation as opposed to image generation on narrow classes. Okay, this is all great. And one common foundation for both of these models is that they were trained on really large data sets. So like several hundred million images, especially 3 years ago, was a lot. And the catch for us looked like an open source AI was that there was nothing even comparably close that we could use as a like stand-in for large image text pairs at this scale. Cool. So in this part, we look at 2 steps we took in order to build better public data sets for multimodal learning. The first one is this Lion 5B dataset, and then the second one, this is the benchmark, the evaluation for datasets they want to build up to, which was the first data-centric ML benchmark that led to state-of-the-art. Cool. Okay, so let's start with Lion 5B. I'm sure many of you have heard of this dataset. This was a super fun, large open source collaboration, lots of people involved, from lots of different institutions, all coordinated by a Discord. And as the name suggests, like the goal here was to build a billion-scale image text dataset. Specifically, we had about 2.3 billion English examples, 2.3 billion multilingual, and then 1.3 billion that were not language specific. Like think of a picture of Paris, if you capture Paris, is this German, French, or English, doesn't really matter. And the key point was that with Lion, we finally had public training sets at this billion scale. So you look at the English subset, 2.3 billion, which is sort of like the same range that OpenAI and Google were in with their aligned basic models. So like previously, the biggest public image text data set was 5cc. Technically speaking, 100 million image text pairs, but if you filter down, like they did in the CLIP model for training, then you had about 20 million images. Okay, cool. But how did we build this? Like basically all large AI datasets, the starting point for this is common crawl. Probably one of the most important projects in AI, public crawl of the internet. And what we started from in common crawl specifically were the image tags, right? HTML has image tags with the associated alt text. So the alt text in the image tag is the text a browser shows if they can't actually load it. In order to have something there, they show the alt text. So on average, this is pretty normal. Most of the time, browsers can actually load the image, and so the alt text is not something that people put too much effort in often. But the good thing is, if you have 50 billion image text pairs, even if it's pretty noisy on average, you can often find like a decent quality subset. And in order to find this decent quality subset, we built up this multi-stage filtering pipeline. The main part of this pipeline really was this content filtering. So what we did here was use one of the existing CLIP models from OpenAI in order to basically weed out bad image text pairs. We took an image with the corresponding alt text, fed them through the image and text encoder, and then we looked at the cosine similarity between the image and text encoder. And if the two were close, like if the cosine similarity was high, we kept the image, otherwise we destroyed it. And yeah, so like this was the starting point. And the obvious question now is again, evaluation. How do you actually make sure that this data set is good? And we thought, okay, in the end, and a machine learning training set is good if it enables training a good model. So we will start with training smallish CLIP models, a B32 size CLIP model. And when you train it on Lion, it's almost the same accuracy as when you train it on, when OpenAI trained it on the N30. So maybe a half a percentage point worse, but this was fantastic. Really nice starting point. And one of this paper board that works 2 years ago, and it has become the training set for many state-of-the-art. Okay, like obviously stable diffusion, probably the most famous thing trained on Lions. And then in my group, we built OpenClip, which has become sort of like the standard open source clip implementation. It's become widely used as that. It was built by Gabriel and Mitchell, who get 2 amazing PhD students. Unfortunately for me, fortunately for them, they have graduated now. but yeah, this is really their right. But we are going to continue here with the lion story. Okay, this is the great part here. We've meshed open here. There was a catch-up. As we scaled up our models and we trained larger clip models, we realized that the gap between our training set, between Lion and the OpenAI training set, continued to grow. So if we train a clip model of size L14, now you are 3 percentage points worse on ImageNet, and you're 9 percentage points worse on ObjectNet. And especially this sort of like annoyed me because I cared about these clip models a lot because of their out of distribution generalization, and now we're losing 9 percentage points. That's not great. So the question was, what's going on? How do we build a better training? And as I mentioned in the beginning, this is not something you can easily look up in the literature right now because there's relatively few work on data curation for multimodal data sets. So we thought, okay, if we don't know what to do, let's set up a rigorous benchmark so we can evaluate what works and what doesn't work for building image text data sets. Okay, and this then led to this DataComp paper. So DataComp stands for data competition. And the idea here was, let's build a benchmark that allows us to do rigorous research for data curation with a focus on multimodal models. Again, this was with many great collaborators from UW, Apple, Tel Aviv, Columbia, AI2, Lion, Hebrew University, UT Austin, and so on. Cool. Okay, and so the idea was we had just sort of like build Lion 5B. And when you build these large data sets, there are so many ad hoc choices. And so we were thinking, okay, let's just redo Lion from scratch in a fully reusable way. So this is not like a one-off dataset effort that you can't really redo, but really let's have a more mature pipeline that we can build many Lion-like datasets to see what does best and do rigorous operations there. And then we were thinking, okay, if we're putting all of this tooling around, or putting all of this tooling, let's set this up as a benchmark, hence the name DataComp dataset. And so like the idea is that we are transposing this traditional machine learning benchmarking paradigm, right? At the beginning, I mentioned that typically machine learning benchmarks have a fixed data set, and then you improve the model. And now we are flipping this around. We are saying, okay, now our model training code is fixed. We tell you exactly how to train a clip model. The only way you can make your clip model better is by improving the training data. And then we know when the clip model gets better, it's exactly because of the training. Okay, and the idea is, if we can sort of like set this up nicely, hopefully we can get a similar nice collaborative research process that leads to better data sets and similar to what we see on the model side. It's a community improve on benchmarking. Okay, well, this is a high-level story. What do we actually concretely provide as part of it? Like the core object here, the starting point, is a large pool of candidate images that we got out of Compositional. So we have 4 different competition scales in DataComp, from 12.8 million pool size to 12.8 billion pool size, so a factor 1,000. Depending on how much compute you have, you can pick one of these scales. And then we took care of some basic safety-oriented filtering. Like we take out some toxic content and so on. So you don't have to do them. But apart from that, we did intentionally minimal filtering, where you can be as creative as you want to be and come up with a new pool data curation strategies. And then we also give you the standardized training code and an evaluation test bed of 38 downstream datasets. We are going to say a dataset is good if the clip model trained with the standardized training code gets high accuracy on these 38 downstream datasets. And as a participant, there's like 2 tracks you can participate in. The first one is what we call the filtering track. It is restricted to this candidate pool. You can only train on data that you get out of this pool, and what we provide is a better filtering method that results in a new subset to train on. And if you think, okay, like Compositional is good, but I actually have some much better data over here, maybe it comes out of a diffusion model, or you get it from somewhere else, then you can also participate. This goes into the bring your own data track. You can supplement this Compositional pool with your own data. Cool. Okay, so this is the framework, and then we were curious, like with all of this in place, can you actually use this to build better trainings? And so we experimented with this ourselves to build a baseline, and the answer is yes. So this is the same table as before. We are training large club models at 15 size, and now on DataComp, you're actually better than the numbers from the OpenAI paper. Specifically, on ImageNet, we have a 4 percentage point gain over the OpenAI training set, and on ObjectNet, we have a 5 percentage point gain. So to the best of our knowledge, this was the first training set that improved over the training set from the paper, and this has become widely used already. Like for instance, and Apple is one of the companies that have built on this for some of their internal training sets. Cool. Okay. And one other way of looking at this improvement is in terms of compute efficiency. So back in the Lion days, before we had DataComp, we could train a model to 79% image accuracy. It just took us a lot of compute. We had to train a substantially larger model for substantially more steps. Now we can get to the same 79% accuracy with 9x less compute. Okay, so let me tell you a little bit about what goes into the baseline here to get a sense. It's about 1.4 billion images in the subset. And so like the main point here was that we like tuned the clip filtering in a better way. So similar to Lion, we started with clip filtering because we knew this was already getting us pretty far. And one thing we found was that simply this threshold at what point you count an example as good versus bad was set optimally, not optimally in Lion. Back when we did this for Lion, this was a bit ad hoc. We just looked at our notebook, what looks good, what looks bad, and we get to stringent. It turns out that being more permissive, including more examples, is actually good. So here, x-axis is the fraction of the pool that you keep. Y-axis is the performance you achieve on ImageNet, or this average over 30 data sets. Like, and you see here that there's an optimum around maybe 25 or 30%. Okay. The next change that we made compared to Lion was no explicit language filtering anymore. So in Lion, we sort of like had a language detector, say, oh, this is English, this is not English. And it turns out language filtering is in itself a noisy process. And the clip models know relatively well what they understand and they don't understand. So if you just do the clip filtering, the model is already decently good at figuring out if it understands the piece of text or not. If it's a language the clip model doesn't understand, then you have a load of it. And then the last bit here was a little bit hacky, and I don't want to dwell on this because we don't use this anymore in better data sets. We also did some image clustering to rebalance different image clusters. This helped a little bit in DataComp 1B, but then in follow-up work we don't. Cool. Okay, so this is one aspect here. What did we actually do to improve the layer? Another important aspect of DataComp is the multi-scale, right? Training a large clip model is pretty expensive. Like a clip VLTL from scratch is about 40,000 A100 hours. And obviously this is quite expensive. You can't just try out new ideas cheaply if you have to train a large clip model. And so what we did was have these smaller scales here, pool size 12.8, 128, and so on. And then the key question is, if I do experiments at a smaller scale, is this actually informative for finally training a large model? Is the performance at small scale and medium scale correlated? Is the performance at medium and large scale correlated, and so on? And the answer is this looks pretty good. Like here, we have ImageNet accuracy evaluated at the small scale, the ImageNet accuracy for the medium scale, so small pool, large, medium scale pool, and every large here corresponds to one filtering method you can apply to the pool. You can apply this either on the small scale or you apply it on the medium scale. Then we record the performance, put the marker in the plot, and overall it's a pretty clear trend. Some points are off the trend line. It's not perfect, but overall this was informative enough for us that we did most of our experiments at medium scale, maybe 1 or 200, and we did only 10 experiments at the end at the large scale. So by the time we started the larger training runs, we were pretty confident these are actually good ideas now, because all the bad ideas we weeded out with the cheaper experiments at the small scale. Okay, cool. So this was what was in the DataComp paper, and then one interesting to see was that the community picked this up and figured out more cool sort of like innovations in dataset design. One of them is this very nice paper from CMU, from Siku and Aditi's group, where they specifically looked at how to handle text and images. So it turns out that the clip models really like doing OCR. If you have an image with some text in the image written, and then the text in the caption is the same text, this gets a really good clip score. A model loves doing OCR, which is interesting. This is not ideal if you do clip-based filtering, because you don't want that most of your data set is OCR if you actually want to do image recognition for things like recognition. And in this paper, they have a nice way of masking out text and images in a good intelligent way, so you get better performance, about 6 percentage points in the medium scale data. This Seahawks group, Santa Cruz, they are really great in model design, coming up with better clip architectures, and they trained a state-of-the-art clip model at the time by just taking the modeling innovations and then training on DataComp instead of live. So we also saw performance gains by training on DataComp. And then the third thing, this is something now one of my students worked on, is around synthetic data. When you do the step filtering, there are quite a few images that are perfectly fine images. They just happen to have a bad alt text, so an uninformative caption. And then it's a little sad because you have this nice image and your clip filter throws it out. Even though the image is perfectly fine, you just don't have a good caption. And then the obvious question is, can you improve this process by having a synthetic captioning model, come up with a caption and be used instead of the real caption from the web? And the answer is yes, you can do this, and this helps in many cases. So details on this paper. And so like just recapping what happened over the past year in DataComp, this is like this current leaderboard table. So like these entries here at the bottom are Lion 5B style filtering, and what we did in DataComp is our baseline. And that gets 27 or 30% of ImageNet. And so like the best thing as of now is this combination of hype sampler plus DFN. DFN stands for data filtering networks, and that gets a total of 8 percentage points better at the medium scale. So I'm going to tell you a little bit about DFN now in the last 2 minutes. How many minutes do you have done?
I had 10 minutes.
10 minutes. Okay, let's do 5 minutes and we will 5 minutes. Okay, cool. Good, data filtering network. So this is a very nice paper. Alex, one of my students, wrote with Vaishal. Alex was interning at Apple summer. And so like they wanted to, well, they studied dataset design also. And one question they were asking in particular is, typically when we do data curation from the web, we start with something like comment crawl, and then there's a complicated pipeline that involves various heuristics, handwritten rules, some model-based filtering, and then you have your training set. And what they wanted to do is just replace everything here in the middle, this entire pipeline, with a single neural network. So there's going to be a single neural network that decides whether to include a data point or not. That makes sense. And the obvious question now is, how do you train this single network? And this is sort of like one of the key insights here, that you first train your data filtering network specifically for the task of image training data filtering, and you do this only on high quality data. And this is important because surprisingly, training a smaller model on less high quality data works better for training the filtering model than training a large model on a lot of data with more noise. So taking a step back here, when we did Lion 5B already, we were hoping the following would happen, right? So Lion 5B in this dataset creation process has a clip model. So we thought, okay, this is going to be great. So we have our pipeline with a clip model. We train a better clip model with our Lion dataset, and we can take the better clip model, put it back into our pipeline, get an even better training set, train an even better clip model. And so this nice feedback cycle, we get better data sets and better models. And then in the end, we have 110% of image. But this did not happen, unfortunately. In fact, this never even started. It turned out as we made the models better for ImageNet and other downstream tasks, they never improved as data filtering models. So like the quality of the resulting training set was basically stuck. And so like Vaishal and Alex had this nice insight that if you want to improve this filtering model specifically, you should train only on high quality data. It's okay if this is less data, but only train on high quality data. And then you can basically lift the the model that understands what is high quality data, and you can lift this to your entire unfiltered web training pool by applying this data filtering network on all of your data. Then you have your final training set at the end, and then you can train a really good model with this final training set. It's going to be really good at the downstream tasks. And to make this a bit more quantitative, This is a plot for looking at this as a compute versus performance trade-off. X-axis is total compute we put in. Y-axis is again dimensional zero-shot transfer accuracy. And then the blue curve here is what you get if you train on Lion only, and you can push up the compute more and more. Models get better, but there's definitely diminishing returns. In the red line here, these are the models from OpenAI. We only have 3 of them, but they definitely have a better compute trade-off. This is what I mentioned earlier. For the small clip models, it was pretty close. As you make the clip models larger, the gap grows. Then DataComp was in turn better than the OpenAI training set, and the data filtering networks is the green line. And at the time, they could train the state-of-the-art clip models like this. 84.4% commission at zero shot accuracy. Cool. So this was all the story here about multimodal learning. There's one last slide before the conclusions. I just want to share this like set of results here with you. I'm very excited about this. We just put this on archive yesterday. So this is basically this entire DataComp framework again, but now applied to language models. So after we did this, we convinced ourselves multimodal learning. There was a lot of room for improvement on the training data side. And then the question was, can you also improve in other AI domains by building better training? And the answer is yes. This is again a compute versus performance plot here. X-axis is training flops. Y-axis is an average over natural language understanding tasks. Here on the right, specifically MMLU. And then the orange line here is the baseline from our DataComp for language models. And the nice thing is that it's really comparable at the 7 billion parameter scale. We get comparable performance to models like Mistral or Llama 3, the 8 billion parameter model, but we use substantially less compute. So we couldn't afford training for 15 trillion tokens like MetaBit, but the cool thing is that when we train for 2.6 trillion tokens, so for 6.5 times less compute, we get almost the same performance as the Llama 3 one. So I think then again, this is only the beginning. Like we have a lot more ideas to try here. I think there's a lot of room for improvement in data curation for language models. Cool. Okay, so let's wrap up. One lesson for me from the past 2 years has been the datasets are a key driver of progress and multimodal learning. We've seen this for CLIP with reliable generalization and retrieval models and text-guided image generation. And there's still a lot we don't understand for how to build good training sets. A lot of these training sets are proprietary, the techniques are ad hoc, and I think this is a great research direction at the moment for asking what makes a training set good. Right at the moment, this is all very in depth. I can't tell you why the data set is good. I can just tell you if I train on it, the numbers go up. But what actually makes this training set good would be important to understand, because then we can probably do more targeted data filtering. Cool. Okay, these are the 2 projects I mentioned, Lion 5P and DataComp. Thanks for listening, and happy to take questions now.
Thanks for this great talk. And I believe the data filtering network is indeed very, it is very great and inspiring. But I have a specific question regarding how to measure the quality of data sets. As you have mentioned before, obviously from this talk, I have known that you may use the accuracy on some downstream evaluation. But my question is, can you directly measure the quality of the data set without even training a model?
I mean, I would really love to. At the moment, I can't. I don't know. I mean, I think this is a really good question, and I think hopefully you will understand this better, and then develop better data filtering models at the moment. Yeah, as I said, like the only way I can really tell you how good this is to train on it, and then. Yeah, I mean, okay, like let's be a little bit more specific. Here, when we say high quality data, what makes this high quality? This was not like text, but this was sort of like captions that humans have written to describe an image, and there's a lot more human review with this. Right? When you do unfiltered web data, there's like no one has verified the captions. Here, there's some human creation. But exactly what aspect of it is now the humans paid attention to, I don't know.
I see. Okay, thank you.
Thanks. Please.
Thank you. Super great talk. I have one question. So when we have, for example, that data filtering network there, I imagine that there are some sorts of data points that get dropped. Have you worried about, for example, fairness and dropping data that you actually want and that perhaps the same MMU or things like that won't capture?
Yeah, sorry, we're not trying to cut off your question. This is a good question. Yeah. Okay, like obviously, yeah, this is a good point. When you have this data filtering network, this may bring down biases into the data curation process. And again, like, do I know to what extent this like helps or hurts? Not in as much detail as I would. But now, one thing that I do want to mention is that when we build DataComp, we do have 38 downstream tasks, and some of them are specifically parameter. And now this model that does well, that comes out of the data filtering networks process, that's not only state of the art on ObjectNet, but it's also state of the art on GOD. This is a nice data set from the Olvers group in Princeton, where you specifically build a test set to measure image classification performance in a geographically diverse way. So it's not just US or European pictures that we test on, but something more globally distributed. And this data filtering network clip model is also the best among the clip models we've seen on GOD. So again, I can't tell you why it is, but generally my impression if you think that the numbers also like go up together. This is not more.
Okay, yeah, go ahead.
Thanks for the great talk. I do feel that the data is like key driving factors for that, which is the whole field forward. And I'm curious about like what might be the next important step for the general field. Like we have like image and text like paradigms right here, and we know that like science data, like medical data, and all this kind of like now currently harder to access data is also very important for the domains to move forward. So I'm just like hoping to hear your insights about that.
Yeah, no, this is a very, very good point. So at some level, when we do this research for language understanding and computer vision, we got really lucky because there's so much data. Like none of this would be possible without the internet as a source that we draw data from. And I think now when we talk about other fields of science, I'm actually not an expert at this. But obviously, you first need to make sure you have these large data repositories. Just being so like that as an observer at a high level, I think it is indicative that probably the biggest breakthrough of AI in science has been AlphaFold, so protein structures. And my understanding is that specifically in structural biology, they have been very good at building large protein structure databases. And once you have all of this data in one place, you can do amazing AI on top. But if you don't have the data in the right place, the right format, then you can have super smart ideas. It's not going to help because at the moment, all of the stuff we do is the very data. So I think in some fields here, the challenge may be less. Let's figure out how to do the data filtering, and more like let's actually make sure we put all the data together and do really allow data.
I see. Thanks.
Let's thank our speaker again.
Next, we have Krishna. Krishna is an assistant professor at the Paul G. Ellis School of Computer Science and Engineering. His research lies at the intersection of computer vision and human-computer interaction. His research has received Best Paper, Outstanding Paper, and Orals at TVPR, ACL, CSCW, EURIPS, and ECCD, and has been reported by Science, Forbes, the Wall Street Journal, and PBS Nova. His research has been supported by Google, Amazon, Cisco, Toyota Research Institute, NSF, ONR, and Yahoo. He holds a bachelor degree in electrical and computer engineering and in computer science from Cornell University, a master's degree in computer science from Stanford University, and a PhD in computer science from Stanford University.
Oh.
Okay. Okay, looks like it's working. Okay, thank you everyone for being here. I'm very excited. So many people are excited about model evaluation. So hopefully this talk will be fun. I'll hopefully have something for everybody. The mic doesn't work, but that's okay. So today we're going to talk about the past, present, and future of vision language evaluation. And I'm really excited that I'm following up Ludwig's great talk because we're going to start out with some slides from some screenshots from his paper to begin with. So there's been a lot of great excitement around vision and language over the last couple of years, especially because it seems like things are working very, very well. And it seems like things are working very well in a very zero-shot manner. We train these models on the internet data that Ludwig talked about, and then we sort of reuse those same models to see how well they perform in a bunch of downstream applications. And the results look very good. In fact, they look so good that you start seeing plots like these, where as you start scaling up the number of data points or the number of classes, things start improving more and more. Or you see plots like this, where again, the more sort of larger your models get, again, the plots seem to indicate that data is just helping a lot and models are getting better and better over time. And even online, everyone's abuzz with just excitement over all the things that you can not only understand, but also generate with a bunch of these generative models. However, it doesn't really explain how we're still feeling like a lot of real world use cases and why these errors keep popping up whenever they do pop up. So for example, if you ask a model to generate an image of one brown pen and one orange leaf, it doesn't really do that properly. Or if you tell it to generate two pens and two sheep, it's never seen sheep and pens together, and so just hedges and produces three sheep instead. And so it fails in ways that we don't really expect, and we don't really have good metrics to try to figure out what's going on. So today in this talk, I really want to talk about how we can go about understanding where these models fail, how they fail, and what we can do about it. So we'll be talking about all the ways we can motivate things that are going wrong in our evaluations that we have already, how we can go about fixing it, and I want to sort of put forward the vision for how we sort of should be doing evaluation moving forward. Okay, and at the core of this idea of today's talk is going to be thinking about what makes human vision so good and being able to generalize all over the place in all kinds of use situations. I can show you pictures that you've never seen before and people doing things that they've never done before, and yet you understand them, you can compose all these ideas together, and fundamentally what's behind a lot of our capabilities is this idea of compositionality, our ability to compose individual units together to make sense of the world that we live in. So even if the things that you're looking at you've never seen, you've seen those individual atoms, and you can compose those atoms together to make sense of the world. So today, to understand how we should go about doing evaluation, I want to sort of start out with thinking about what is the right representation that we should be thinking about in computer vision when sort of evaluating models. And then we're going to build that representation. And once we have that representation, we're going to talk about how we can use that representation to evaluate today's best models. And spoiler alert, we're going to show that none of our models are compositional. And then we're going to talk about how we can draw ideas, again, from humans and how we sort of have a compositional visual understanding and compositional language understanding, and then move on to sort of building better and better, more useful models that work in the real world. Finally, we're going to switch gears. We're going to talk about not just understanding, but also generation models. And again, do the same thing. We're going to talk about how those models are not compositional and how we can go about improving it. And then finally, if we have time, we're going to talk about how the future of benchmarking should work, going beyond compositions. Okay, so tall order, let's see how far we get. So to make sense of what is a good representation for computer vision, let's sort of motivate it with this image, these two images. You've got two images that have two people in them. Now, if I take away the pixels and just look at the objects by themselves don't really help you a lot. They tell you that there's two people in the image, but you might assume that just because there's two people, the semantics behind those two images are the same. But in reality, those two objects might be doing very different things. In one image, you've got one person that's angry and yelling at somebody, and in the other case, you've got one person paying attention to someone else. So the pixels really give you a lot of semantics behind what's happening beyond just the objects themselves. So this idea behind going beyond objects is something that's fundamentally been around in cognitive science for many, many decades. One of my particular scientific heroes, Irving Biederman, in the 80s, he was doing a bunch of experiments trying to understand how people make sense of the world. And one thing that he found was that if you violate some attributes or relationships in images, then it slows down our ability to process what we're looking at. So for example, in the first image, you've got a person that is transparent. And because that person is transparent, you take longer to recognize that thing as a person. In the second example, you've got a fire hydrant on top of a post box. And again, it's the same problem. You are slower at processing and identifying the post office box and the fire hydrant because that spatial relationship is not one you're used to. And he concluded that beyond just understanding objects, we're basically processing attributes and relationships in parallel to recognizing these objects. And so with that sort of framing in mind, about 6-7 years ago, we developed the scene graph representation. And in that representation, we took every single image. And of course, we annotated them with objects. You've got the individual object in the scene. But we also added in all these attributes associated with all of these individual objects, and then connected all those objects together using pairwise relationships. Now, this is a very, very small scene graph associated with this particular image. And to sort of really further studies in scene graph understanding, we developed the visual genome dataset, which contains a ton of these graph representations that are very, very dense, associated with a bunch of different images. Okay, so over the last 6 to 7 years, people have been developing a ton of scene graph generation models, and they're using it for all kinds of different purposes. But in today's talk, I want to use it for evaluation. Okay, so let's switch gears now. We have a representation. We have a scene graph representation that allows us to understand and recognize new scenes as a composition of things we've seen before. Now let's use that to evaluate whether the models we have today, whether they are compositional or not. Okay, so let's think about how we're going about evaluating models. So if you take a traditional vision language model, the way you evaluate it is you're given an image query, and you ask the model to retrieve the correct caption associated with this image. Now, of course, in this case, you might want the model to retrieve this particular caption that says that there is a yellow vase on top of a black television. Now, this is a very, very simple task if you only are looking at the caption. But of course, you usually give a ton of different negative examples, negative captions associated with a large data set. So you want to make sure that your model picks the right caption and not all of these negative ones that are also in this large pool. Understanding and being able to retrieve this is very similar to compositional understanding, because in order to retrieve the right caption, this model needs to be able to identify that there's a vase, that there's a television. It also needs to identify that the vase is yellow and that the television is black. And it also needs to understand that the vase is on top of the television set. Okay, so essentially what we're testing for is this scene graph representation associated with all of these images. Okay, the problem with all of our benchmarks is that this is too easy. The reason it's too easy, because if you look at all of these negatives, you know immediately they're all wrong, right? There's no giraffes, there's no panda, they're just very easily and obviously wrong, right? And so even though our models look like they're doing very, very well on a bunch of these benchmarks, it's just such an easy benchmark to beat. So to actually provide a fair evaluation for whether models are compositional or not, we developed a bunch of different benchmarks over the last couple of years, and they all fall under the umbrella of CRAPE-like benchmarks. We created CRAPE, Sugar CRAPE, and a bunch of other ones. So let me give you an idea of exactly what CRAPE tests for really quickly. It tests firstly for systematicity, which is basically saying that if in your training set, you've seen examples of vases and the color pink, in your test set, you should expect your model to be able to understand pink faces. Okay, so the combinations or compositions of atoms that are unseen during training, your model should still be able to recognize those specific compositions. That's what it's testing for. The other thing CRAPE tests for is productivity. And by productivity, what I mean is that if you have compositions that are growing in size, so in complexity, so for example, you've got complexity 4, which means that there are 4 different atoms in your caption, or complexity 10, where you've got a ton of different atoms that are all put together under one sort of caption. So can your model still recognize things, even though the complexity of the images, the complexity of the captions are getting more and more complex? Okay, so to really evaluate models on this task, we have to generate a lot of negatives, and these negatives need to be hard. They need to be testing for compositional generalization. And so this is not going to be it. We can't use the existing captions that are out there because they're too easy. So instead what we do is we take the ground truth caption and we alter it. We alter it in a way to produce compositional hard negatives. So for example, we change the yellow vase into a red vase. Now your model should really not be picking the red vase because that vase is yellow. Or we can change one of the other objects. We change the television to a table. or we can change and alter the relationships. We can change it from on top of to next to. There's a bunch of different altercations that we can do. And anytime we make these changes, it only works as a negative if it modifies and changes the semantic meaning of the word, of the sentence, so that it's no longer a true caption for this image. So to do this, we parse a ton of data sets, including the Lion data set, conceptual captions, and many other data sets. And we parse all of their captions into objects, attributes, and relationships so that we can start building out these sort of seen and unseen splits that clip models have been trained on. And so we do this across many different data sets, and we produce a ton of evaluation sets. And these evaluation sets are not small, they're gigantic. There are about 300,000 examples that are being tested for every single model across different training data sets. Okay, so the numbers we get are statistically significant. Now, we evaluated last year a bunch of different models. We evaluated the clip models, we evaluated Cyclip, Flava, Albef, all of these different ones that have been out. We evaluated them when they're trained as transformer architectures or ResNets. We trained and evaluated different sizes of models. And regardless of what we tried to do, sadly, all the results are extremely very, very low. All of these models perform very, very close to random chance on a bunch of different tasks. In fact, from our evaluations, we found that the best models are performing at about 32% accuracy in it being able to retrieve the right caption. And this is not great because random chance is about 25%. Okay. Now, we might expect to see curves like this if our benchmarks are easy, but the moment our benchmarks get a little bit harder, we don't see that really nice curve anymore. We instead start seeing that models are overfitting. They're getting better at the things that they've seen. They're getting better at the seen compositions, but the moment you test them on the unseen compositions, the gap gets larger and larger. And they get larger as the models increase in size. They get larger as the data sets increase in size. If you look at productivity, as the complexity of your captions increase, things almost approach random chance or are at random chance across all of these models. So they're getting really good at memorizing data, but they're not getting any better at generalizing to the real world at all. And these trends hold regardless of how large of a training data set size we use. Even if we train on smaller data sets like conceptual captions or larger ones like Lion, it doesn't matter. They're all around random chance. In fact, even if you train larger models, it's still the same. So things are not very good. And you might ask, maybe this is a problem with the synthetic data, the synthetic nature through which we're collecting these sort of hard negatives. Maybe that's what's causing these errors to happen. And so to make sure that wasn't the case, we have a new collaboration with a new paper that's coming out within a week or so, where we collected real world hard negatives by mining the internet. So we have examples of images with text that alter, again, very similarly as hard negatives, but these are real world images, real world captions, okay, that we found online. And again, the results are really, really bad. Human performance on this new benchmark is about 95%, and most models are less than 10%. Okay, the only exception we found was GPT-4 Vision, which was about 21%, but everyone else is less than 10% accurate, where random chance is 6%. So we have a long way to go. Things are really not actually working. Models are getting much better at memorizing and not doing much else. So that answers the second part, which is our models are not compositional today, and we have a long way to go. So what can we do about it? And so this part of the work was done by some of my amazing PhD students, Jixian, Shengyu, Jieyu, and in collaboration with CMU professors and students as well. So what can we do about it? So one thing we can try to do is draw inspiration again from how humans develop a compositional understanding of the world that we live in. And so over the last couple of months, my group has been releasing a bunch of different methods-based papers trying to induce compositional understanding into our models. We've been exploring data-centric methods. We've been developing data sets that can actually induce this kind of behavior. We've also been introducing new architectures that can actually decompose concepts and make things work better. And we have also been developing new algorithms to sort of make this happen. Now, I don't have time to talk about all of them. This is, in fact, a evaluation workshop, but I do want to focus on at least one of them so you get a sense of exactly the kinds of things that we're doing in my group to try to induce compositionality. This paper draws inspiration from a bunch of human studies. So one of my favorite cognitive scientists is Simon Kirby, and over the last 20 years, he's been studying how do humans develop a compositional language. And he's been doing this by actually getting people to develop languages. And one of the things that he's been doing is he brings people into rooms, and they're only allowed to communicate using a restricted communication symbolic language. And one person sees a stimuli, so it sees this triangle, that's the director, and the director must now convey what they're looking at using these restricted symbols to a selector or matcher, and the matcher must pick out which one the director sees. Okay, he continues this game, and this game is called Lewis signaling game. It's a type of game that's been around since the 70s. And he finds that regardless of what you try to do, people never generate a compositional language. No matter how long you keep people in that room, they end up learning and memorizing a language, and that language is not compositional. To give you an example of what kind of languages people build, here's an example stimuli, and here's a word associated with that stimuli. And here's a dictionary for a type of language that people create. Even though a lot of these things are compositional, it's got arrows and shapes, the words are not compositional at all. And he tried for many, many years to try to figure out how to get people to generate a compositional language, and they just never did, until he figured out one fun hack. The thing he figured out was cultural transmission. So what he did was he let people generate a language, they created a language, and then he would replace one of those two people with a brand new person. And that brand new person came in and must now learn a new language from the person that's remaining. And then he replaces another person, and then replaces another person, and continues this replacement process over time. And if you do this in your study, turns out your language starts becoming compositional. So suddenly you have shapes, and you've got arrows, and they all have languages that compose different components and symbols together. So your language that people start building starts becoming compositional. So the sort of conclusion that he comes up with is this idea of cultural transmission, this idea that the need to teach our offsprings, the need to teach the next generation, that's what creates compositional representations. And the reason for that is because the compositional language is the easiest language to learn. Okay, because if you understand the individual symbols, you can put them together and generalize to a lot of different use cases. We operationalize that in the CVPR 2024 paper. Come check out our poster later on this week. And in that paper, we reframe the common way that we typically train models using especially CLIP models as this Lewis signaling game, where you have a language agent and an image agent, and they work together to build a representation. Now, what we do over time is during that training process, we just randomly replace one of those agents. We just reset their weights back to 0 or back to random initialization. And we replace, keep doing this replacement over and over again. And we, of course, add in a restricted symbolic representation using a sort of code book in between. Now, if you do this over and over again, there's some interesting things that start happening. So let me talk to you about exactly what this algorithm looks like, because it's not as simple as just replacing these agents and resetting their weights. You have to do a little bit more. So first of all, you have to restrict their language so that they're not open to generate any kind of representations, but we have a code book, a discrete, finite code book in between that they can exchange representations through. And once you have that, you train them for a little bit, and then once you are ready to replace one of these agents, what you do is you actually do a distillation step. You do a distillation step for a couple of iterations, not too long, just a couple of iterations. So if you replace the language agent, you want to distill from the older generation for just a little bit. Think of this as like your parents teaching you the language, and then you let them out in the world. You let it go interact with the vision agent that's not been replaced. And you repeat this process over and over and over again. And if you do this, this is what your training curve looks like. Every time you replace one of these agents and reset their weights, suddenly, of course, your loss jumps up, but you'll notice something very interesting. The loss comes back down really fast. It's not a completely new training process. It almost as if it never got replaced, the entire loss keeps going down organically. So with this sort of training algorithm, we found that systemicity performance on CRAPE actually goes up quite significantly, from 33% to 45%. Now, of course, these are small models that we're training. These are VIT bases and larges. We can't go to huge because we're an academic lab, but at least for these kinds of models, we're seeing that this kind of training algorithm improves quite a bit. And not only that, it also learns downstream tasks faster. Again, because their representations are compositional. And so because they're compositional, they can adapt to new downstream tasks faster. So you need fewer training iterations to adapt to ImageNet afterwards. And it doesn't perform any worse. Even though you have a restricted codebook representation, it does not reduce its performance on ImageNet. Okay, so what's actually happening from a machine learning perspective? We are still trying to figure it out. So come chat with me. We're trying to figure out exactly what's happening from a theoretical point of view. We know that self-distillation, which we're doing, does induce some amount of smoothness into the model. And maybe that's producing some sort of a high-pass filter into the learning process. But I would really like to dig into exactly what's happening. Okay, so we've been trying to do these kinds of algorithms, and that sort of is the third part of this talk, where using cultural transmission and ideas from human vision, we can actually build models that become more compositional. Okay, so let me sort of switch gears a little bit. And before that, yes, collaborators. This one was led by, again, some of my PhD students, Chen Hao, Cheng Yu, Jie and Amita, and also in collaboration with Aaron Corville and Ankit from University of Montreal. Okay, so let's switch gears. We talked about understanding models for a little bit. Let's talk about generative models, right? So we have the same problems happening in generation models today. You've got these models where if you tell it to generate a photo of 3 dogs, Stable Diffusion gives you this stuff. Sometimes it gives you 2 dogs, sometimes it gives you 4 dogs, sometimes it decides, you know what, it'd be nice if there's a little child in there too. But it just doesn't give you what you actually want. And other times you might ask it, hey, I want a photo of a refrigerator with many different items on top of it, and it just doesn't know how to do that. For whatever reason, it keeps generating refrigerators with items inside of it, not on top of it. And again, it just doesn't have this compositional understanding of these individual atoms. And the problem is, we are not evaluating these models the right way. The way we're evaluating these models is using CLIP score. And we just talked a lot about how CLIP is not compositional at all. And so if we're using those to evaluate our generative models, we're basically hill climbing on noise, right? And so if our model generates something and we evaluate it with CLIP, CLIP will tell you something. It doesn't mean anything for your actual evaluation. So how do you actually go about building good evaluation systems? People have tried a bunch of different things. They've tried to turn that generation into a caption and try to evaluate that caption. That doesn't work very well either, because captions only capture a small part of what's in the image. So it's not good enough to evaluate everything that your model is generating. So how do you do it? Well, to sort of motivate what we did, let me give you an example. So here's an example thing that we want our model to generate. We want it to generate an empty bedroom with a flat screen TV sitting on a dresser. And it gives you this. Now, immediately, you all know what's missing. It's missing the TV, right? There's no TV in there. How do we turn that intuition into an actual evaluation framework? The way we do it is by introducing this framework called TiFA. And what TiFA does is it takes that input text and it uses an LLM to generate a bunch of questions that it should be able to answer from just the text. So for example, is there a TV in the room? And then of course, because it can generate the question, it can also generate the answer. And so you've got these question answer pairs. Now you can take that same question and ask a model, a visual question answering model, if there's a TV in that image. And it'll tell you that there's no TV there. And by comparing the answer that you get from the caption versus the answer you get from your generation, you can actually build very intuitive evaluation frameworks that'll tell you exactly why this image is not a good image. It'll tell you what's missing and how you should go about fixing it. So we developed a bunch of different methods over the last couple of months, again, on improving this metric. We take every single caption that you feed in, we extract all the objects, attributes, and relationships, we turn them into a bunch of questions, and then all of those questions now serve as fine-grained evaluation for your generation. And using this, we can directly identify, yes, our models today, they're terrible at shape. Anytime you wanted to generate a specific shape, they fail. They're terrible at counting. This is something we all know already. And they're also really terrible at spatial relationships. These are things that our models today are just unable to do. And if you look at evaluating these things as your caption gets more and more complex, things drop quite a bit. The moment you add in more atoms that it should add into your generation, again, we can evaluate them and we can see that there's a big drop in performance the moment you increase the complexity of what you want to generate. Okay, so now that we have an evaluation metric, we can use it to actually improve our models. And so we developed this method called DreamSync, where given any text input, we sample a bunch of different images from our generation model, and then we evaluate all of them. We can evaluate them with TiFA, or anything else that you like, as long as it's something that is actually a good evaluation. And when you do that, you can identify, okay, what are the good generations that are faithful to my input? What are good generations that are aesthetically pleasing? And you can use those as reward to then do RLHF and select the best and actually fine tune your original text to image generation model. Okay, this method is called DreamSync. And over time, we find that it improves faithfulness to actual inputs. So for example, if you wanted to generate an image of a cube-shaped porcupine, so remember, shapes are something that models struggle with, but by doing DreamSync and actually learning from its own mistakes, over time, every single iteration of training, it actually gets better and better, and it starts producing porcupines that are cube-shaped. Okay, again, this is obviously not in its training data, but it can generate it. And similarly, you can ask it to generate an International Space Station flying in front of the moon, a photo that has never been taken. And again, it can learn how to do that because we're sort of giving it the signal to help choose good generations. Yeah. 3 more minutes? Okay. All right. And finally, here's some other examples. If you get, it starts to learn how to count, it starts to associate attributes correctly. Here you've got a wooden heart and one wooden heart and one marble. And then again, as you train longer, you actually see the improvements happening. And again, you can do the same thing for a bunch of different things. It can generate chairs that are shaped like marshmallows. It can generate cats that have black ears, as well as markings that are that specific color. And I think that's where I'll stop. I won't get into the last part, but the last part basically says that, again, if you have the right compositional representation and the right sort of evaluation metric that tests fine-grained exactly what's in your image, you can start improving these models by developing algorithms to test for them directly. So I'll stop there. Thanks.
Thanks for the talk. Very interesting. I have a question about the TiFA evaluation. So it seems that it depends on the VQA model.
Yeah.
I'm worried that the VQA model might also hallucinate.
Yes.
Based on the way you ask it the questions.
That's right.
Do you think that's an issue or not?
Absolutely. Yeah, you're right. We are basically backing off. We're basically saying that our generation evaluations are not very good, so maybe we can back off to something else. But we do know that our VQA models are improving at a rate that's better than the other sort of models that we have. It's at least good at recognizing individual objects and saying that they're there. It's good at recognizing and answering if a specific attribute is associated with an object. And so they're good enough right now where this evaluation makes sense. And over time, these models will improve even further, where this sort of framework for evaluation will continue to improve. Yeah.
So because now these models are so much worse, we can at least get them to be as good as VQA.
Yeah.
We can probably take one more question.
Thank you. This is a great talk. Really interested in the compositional learning when you're doing the distillation codebook. How did you pick the size of the codebook? Was that arbitrary, or did you have some methodology?
Yeah, great question. For the codebook itself, we treated it like a hyperparameter. And I think at the end, it came out to be somewhere around 128 dimensional vector. And then we just chose from those 128 different vectors that we have in our codebook. Yeah, but we treated it like a hyperparameter, yeah. Okay, little plug. I'm giving another talk at 3:55 about something completely different. Come check it out. It's part of the Human in the Loop workshop.
Let's take our speaker again.
Lên sỏi
Can you hear me now on virtual? Yes, you should be able to hear me. We apologize for the previous talk. We will take care of that in future. Screen.
Hello. Yeah. Good afternoon, everyone. I hope you're having a nice session. Today, I'll be presenting contextual, context-sensitive, evaluating context-sensitive text situational reasoning in large multimodal models. Before we dive deep into the research, let's just look at some preliminaries. What are text-rich images? So images which contain embedded text, which are central in understanding the information conveyed by that image. For instance, memes, documents, infographics, traffic signs on roads, or even a number plate are all text-rich images. So the authors of the benchmarks in evaluating native vision language models on such text-rich images. So we would see one line common across the more commonly used benchmarks like text VQA, doc VQA, and infographic VQA. These benchmarks test the text recognition ability of the model and not other abilities like how can this text interact with other objects. And another interesting fact is if we use a tool-augmented LLM like GPT-4 with a strong OCR model, this method can also answer these instructions. However, a VLM which has access to both image content and the instruction should be able to jointly reason over embedded text and visual elements. And that was the motivation behind contextual. For instance, let's say if you want to predict what's the cost of renting a machine for 9 months, and this machine is given in this image, the model first has to understand which machine it is, which is a front load machine, and then answer accordingly. We see a VLM like GPT-4 Vision can respond to it, but the tool augmented approach fails in this. And thus we came up with some diverse visual scenarios like navigation, shopping, time, reading time using the websites, applications, infographics, abstract scenes like memes, and other miscellaneous natural scenes. And we composed an evaluation set consisting of 506 high-quality samples labeled by humans. And some results are on the left-hand side. So as evaluated by humans, the performance baseline for human beings is at 80%. And the best performing model as of December late 2023 was GPT-4 Vision, lagging behind by 31%. As done by GPT-4 evaluation, because we also perform an automatic evaluation, this difference is about 22%. But if you look at now in June, this difference has dropped down to 7% with respect to GPT-4o, which is the recent best performing LLM. And the second best would be Gemini 1.5 Flash model. Some key takeaways would be like the current LLMs suffer most in the time and the infographics category because of lack of training data diversity. As compared to the open source models like the Lava model, they perform well only in the abstract scenes and miscellaneous natural scenes, again mentioning that there's a lack of training data diversity. Another key point is the encoding abilities. So if we improve the encoding ability, as we can see from Lava 1.5 to Lava Next, and having a better vision encoder leads to better results on contextual, mentioning that improving vision encoding abilities is also important. I'll be presenting the poster in our call. 465 is the number. Looking forward to having more discussions. Thank you.
Yeah, just a sec, I'll find them. This one?
Yes. Should I present?
How we should do that.
Hello? Hi everyone, I'm Jiqiu from Carnegie Mellon University. Today I'm excited to be here to share our recent work on compositional text-to-visual generation. State-of-the-art generative models like Midjourney, Stable Diffusion, and DALL-E 3, Sora are of exceptional quality and realism. However, generating complex prompts involving multiple objects, attributes, and relations remains challenging. For example, even Midjourney struggle with a prompt, the brown dog chases the black dog along the tree. To evaluate compositional generation, we introduced a new benchmark called GenAI-Bench with 1,600 prompts collected from graphic designers. In this process, we found that user prompts often require advanced reasoning skills like logic and comparison. For example, users might want to draw a bookshelf without any books, and an ant carrying a backpack larger than itself. Therefore, we carefully tag each prompt with all associated skills for a fine-grained analysis. This makes GenAI-Bench more comprehensive than existing benchmarks like Party Prompt. Our human evaluations show that models like DALL-E 3 and Gen 2 still struggle on GenAI-Bench due to the lack of compositional reasoning. In addition, we'll release all human ratings to benchmark automated metrics. And we also introduced a new metric called VQ scores that uses a simple yes or no question to evaluate how well an image aligns with the input text prompt. Our results confirm that VQ score outperforms all previous metrics on GenAI-Bench. We also demonstrate how VQ score can improve text-to-image generation by selecting the candidate image with the highest VQ score. This allows us to even improve black box models like DALL-E 3. Thank you for listening, and please check our paper for more details.
Wait. So, I don't see anything. So you are. $11, this one?
Yeah.
Okay.
PDF is fine.
What?
PDF.
Yeah, well, we did some maintenance. And just like this.
Okay. Hi everyone. I'm Leonid. I'm a PhD student at Arizona State University, and today I'll be presenting our work evaluating multimodal large language models across distribution shifts and augmentations. As most of us might have seen over the past 2 days, large vision language models have been developing at a rapid scale. However, a key foundation for them to be deployed in the real world is their performance across distribution shifts. In this work, we try to understand where this type of model stands across visual and language evolutions. In this work, we evaluate 3 open source large language models and 2 diverse data sets. We evaluate on COCO, which is closer to the distribution of the pre-training data of these models, and Clever, which is synthetic, which is farther away from the distribution of the pre-training corpus. Setting up some baselines, we find that performance on Clever consistently remains lower on COCO, despite being a much simpler data set. Interestingly enough, we also perform analysis on the number of objects in an image, and we consistently find that there is a performance drop as there are more objects in an image. This is done in Clever because Clever comes with sub-ground annotations. Similarly, we also perform a baseline study trying to understand if the kind of objects in an image make an impact. We find that if there are same kinds of objects in an image, model performance is much better compared to images which contain a diverse number of shapes. Now we move on to the next setup of visual perturbations. In this case, we apply 6 visual perturbations to a given image and then evaluate the downstream performances. We apply different sorts of noises, zoom blurs, and Gaussian low-pass filters. One of the key findings is that there is a big drop in performance as these augmentations are applied. Performance on Clever is significantly lower than on VQA-V2. However, the drop in performance in VQA-V2 is much larger. We also find that the most harmful augmentation is the Gaussian low-pass filter, which indicates that models do tend to learn correlations from high-frequency regions in an image. We also perform interesting analyses where we find that, for example, on the top row, color-based questions lead to largest drop in performance, whereas shape-based questions do not degrade performance that much. This also correlates to the shape bias that vision language models tend to have. We also present some illustrative results where boxes in red highlight that models get the answers incorrect. As we find across color, number, shape-based questions, failures are evident. Next, we set up a language perturbation experiment where, given an original question, we add logical connectives of the following. We work with negations, conjunctions, disjunctions, and we also create a new category where we add more complex questions. Consequently, we find that as questions get more complex, models' performance tend to go down. Interestingly, we also find that as questions get more complex, models tend to say a yes. So, which again justifies complementary work that maybe these models are treating sentences as just bag of words. To conclude, we believe that there is a large scope of improvement in improving the robustness of these models across distribution shifts, and that this is a crucial parameter to be filtered before they are applied in real-world settings. Thank you, and I also invite you to check our paper and poster, and looking forward to discussing more. Thank you.
Hello, my name is Alon, and I'm going to present what's quantitative evaluation matrices for image editing approaches. Today, a major challenge in image editing research is the lack of quantitative evaluation frameworks, especially for GAN inversion methods. The common frameworks either evaluate the consistency between the input image and the unedited inversion image, or the edited image capability of the inverted image. This issue leads to methods that mostly focus on inversion quality, neglecting editing, and methods focusing mostly on editing while neglecting consistency to the input. Neither method achieves desirable editing. Our approach introduces an initial step towards addressing this issue. We introduce a framework for assisting image editing algorithms. We conduct a user study demonstrating a strong correlation between our proposed metric and human preferences. We initiate a discussion on developing structured methodology for evaluating image editing methods, and we intend to release a dataset for future study. Using a controlled synthetic image generation pipeline, we generate an array of pseudo ground truth images. One of the images is chosen as the base image, which the editing algorithms try to edit to mimic the pseudo ground truth, the other pseudo ground truth images. Then these images are compared to their ground truth counterparts. In the paper, we show how in a controlled environment, the evaluation behaves as expected. Then we demonstrate its application across various algorithms. And finally, we assess its correlation to human preferences using a user stub. Thank you.
So the features present, present.
You don't have to present it yet. So you don't have to present it yet. You can just scroll.
Yeah, that's
Bigger.
faster, right? Yeah. Yeah. Hi, my name is Ramya, and the work is in collaboration with the Indian Institute of Science. I work as a research scientist at PCS in New Delhi. We present a reference-free metric for object erasure. Why is it required? Let us see the motivation. Suppose if you're an in-painter and you use diffusion model-based in-painting method. So let's say you have in-painting method 1 and in-painting method 2, and you have a cute dog on the left with it, which is the input image. And you want to give a prompt like a beautiful empty space with high quality setting, erase the object of interest. So in painting method 1 gives a image on the top, and in painting method gives image on the image at the bottom. So what we realize is, like, if we compute a clip score, use a reference-free clip score between the two images. So you need a reference, and as a result, like, you need to compare if the object is actually deleted or not. So clip score would give a same score for both the in-painting methods, whereas our proposed method gives a different evaluation when the object is erased and object is replaced. So it lacks the current metrics lack the distinction between object replacement and object erasure. So let us see why we conducted one application. You can think of object erasure as a diminished reality, where you are supposed to delete the objects in a scene or erase the objects in a scene which are least interesting. So that's one valid application. And apart from classical in painting, right? So we take the method called SD in paint and try to in paint using 5 different seeds. So you can observe the randomness along each column. So each object is highlighted, and you're supposed to in paint the object, delete the object and replace it by the background to have a background coherence. So so not only SD in paint, but also BD, instruct, pix to pix, glide, and commercial in painters give random outputs when object erasure is invoked. This necessitates a metric for measuring if the object is deleted properly or not. So what do we do is, like, given an image, and we can generate a mask using any model such as segment anything model, and then you in paint, and you extract the feature, split the features using the VIT style of image encoding, and you also have a mask of the object which has to be removed, and then you pass it through the VIT encoder, and you obtain the patches corresponding to foreground and background and do a comparison. So the problem with the existing LPIPS, LPIPS, which is learned image patch similarity metric, is that it needs a reference image. So how do you have a reference image for every millions of examples? So it's not practical. So one of the method has to be reference free, in the sense we don't need a ground truth in order to measure the efficacy of object erasure. So these are the steps of the algorithm. You have the input image, and you pre-process foreground mask, which could be just a random bounding box or a segmentation mask. And you have VIT feature extractor, and a similarity score. So you just compute a cosine similarity between the foreground patches and the background patches after computing the average. We compute this on a toy data set comprising of images scraped from the internet with the diverse backgrounds, and then we conduct in painting. And we measure LP, IPS, and as well as RIMO. We observe a negative correlation between LPIPS and RIMO. So what we intend to say, we also do a diverse evaluation of mass of various sizes and shapes for object removal from using a de facto data set. So what we observe is the existing metrics, which are like clip score, NR is no reference, FR is full reference, as in you have access to ground truth, and LPIPS. So you observe that actually our remove metric has a positive correlation with the human perception. And we also perform a user study. I would be happy to take questions, and our poster is available at 472. Yeah, thanks for your interest. Yeah.
We'll start it with Dr. Leonid Kremlinski, who is coming from IBM Research. He's principal researcher there. And I personally know Leonid from a long time ago when we started our journey in computer vision at the Weizmann Institute in Israel. And Leonid actually defined my career, I should say, because my first oral was thanks to his great review. And so it's great to host him now today at this workshop. Right.
Thanks, Maria. Can you hear me? Okay, cool. Let's start. So my name is Leo. I'm from IBM Research. It's not working again. No, it will be back. It will be back. I'll just try to talk loud. Do you hear me in the back? Yeah, perfect, perfect. All right, so the topic of my talk today will be analyzing and improving compositional reasoning in multimodal foundation models. Oh, it's back. Cool. Comes and goes. So this is, work done with lots of people, some sitting here in the front row. And this is all thanks to them, of course. The slide might not be updated, and the list should probably be longer, but we have people here from different countries, US, Israel, Europe, and other places. All right, so the plan for today is quite ambitious, so let's see how we manage to cover it. It will be mostly about the notion of compositional reasoning, and I'll define it immediately. What do we mean by that? So don't worry if it's not familiar. It's just a term that we like to use. We'll present the term. We'll discuss those issues that we kind of all see, and not just us. Most of the community sees, and even in the strongest vision language models. And we'll present some solutions. So I just tagged them by simple, safe, cheap, lifelong instruction tuning, but those are arbitrary. The plan is just to promote some recent works on this topic, which are all cool. And in the end, we'll ask the question, like, are we there yet, or are we done? And I'll have some insights to share. All right, so let's start. So what do we mean by compositional reasoning? So compositional reasoning in our kind of notion is basically having a model understand the intricate details of language in a visual scene, right? What are those intricate details? So the order of the words, the notion of attributes, relations, actions, states, and so on. So this slide is a little bit old. So this was done when Lava and MiniGPT-4 just came out, but this is still relevant. Essentially, you ask those models to describe a scene or ask some question with regards to the scene. And, the model kind of says the right words. So it says, yeah, there's a child, there's a chair, there's a cat, and there's some arrangement between them. But it kind of confuses, like, who is sitting on the chair, like, what is, each object doing. It's a kind of, saying the words, but not truly understanding their meaning. So this is the compositional reasoning notion. And as I said, it is still present. So this is about, this is from some report that was done like a year ago on GPT-4o. Now we have GPT-4o, but you know, today on different workshops, different people said pretty much the same thing about the most recent models as well. So GPT-4o also has it, and diffusion models have it. So the notion of this compositional reasoning, fine-grained understanding of the scene, is still a little bit lacking. And you know, it's our goal in this line of works, and you know, even the most recent works we just published in archive, is to uncover, you know, this notion, try to fix it in different ways, you know, and see how we keep going. So let's begin. So the first work I'll present, this is the work done with Sivan, who's sitting here. May say hi, Sivan. Right. So and of course a team of more people. So this is a very simple way to you know, treat this problem. So basically, we started with encoder models back then. It was done for CVPR23, so some time ago. So one thing, you know, encoder models are, you know, they are older than the more popular encoder decoder, like you know, models that connect language model decoder to a vision model encoder, you know, and talk to you and chat and so on, like Lava. But still, you know, even those models are based on the same encoder. So, for example, if CLIP has some issue, those models likely, you know, inherit this issue. So this one is focusing on CLIP, and in CLIP, this compositional reasoning problem exists primarily, you know, due to the very simple intuition of the contrastive learning objective of CLIP promoting this kind of bag of words notion for, you know, for representing language. And the reason is, you know, you know how contrastive loss works, right? You get a random batch of images, then you say, okay, so this text that belongs to some image needs to match this image more than it needs to match all the other images, right? But the images are random, right? So like the minimal common denominator that can separate those images and those texts is just usually just the objects in the scene, right? It doesn't actually need to understand the order of the objects, doesn't need to understand additional words like attributes, relations, and so on. Enough to understand the objects, and you almost solve the entire problem. So this is illustrated on the top there, right? So the random texts don't cut it. So what we did is very simple. We said, okay, so why don't we just you know, take this real text and augment it a little bit, slightly, exactly in those notions, you know, that we call the compositional reasoning. So augment the attributes, augment the verbs, augment relations, and just train, add it to the contrastive, you know, objective, and miraculously or not, you know, we got like 15% improvement and almost no degradation because of the way we fine-tuned with parameter efficient LoRa. And of course, the augmentation itself is very simple. You can do it rule-based. You know, you can call a language model to fill in, you know, some masked words. You can paraphrase and so on. There are many ways to do it. So this was the first work. I would call it a simple solution. Then we moved on and said, okay, so this is a simple solution, but it still needs some kind of paired data, right? You need to take paired data, you need to augment the text. So it's maybe less safe because you need to use real images. Also, it's more costly because you still need to collect some paired data. So we kind of challenged ourselves asking, can we do it also with completely synthetic data, right? So let's say the model is there and want to fix the same issue, but we want to do it with collecting synthetic data. In this case, we used you know, physical simulation with 3D world platform to produce synthetic images by some kind of scene randomization, throwing in objects, you know, including people, dressing them in different ways, arranging them in different ways, collecting lots of metadata, and then using language models to convert this metadata, very dense and rich and very accurate metadata, because, you know, we synthesized everything, into you know, long visual descriptions. And to that, we attach some kind of curriculum, right? So we, again, use LoRa, use in the, specific freezing that was found to be best. Additional things like domain adaptation tricks and some handling of long captions, and eventually also ended up, improving. So we have the compositional reasoning benchmarks there. So I haven't introduced those before. We also worked on the same benchmarks in the previous work, like Vel, Checklist, Arrow, and a bunch of others. All of them usually present you an image and a binary choice question. The two binary choices are very similar. The only difference might be in some attribute or verb or relation. And the goal of the model is to recognize which of those sentences is entailed by the image. And there are a bunch of others, but they are all similar in this sense. And we could get, again, very nice improvements at no costs of the generative release of the model. So the zero shot of the model remains the same, right? You can measure it on a bunch of, zero shot variations. And this is nice. So then we moved on even further and then challenged ourselves yet another time. This time we asked, okay, so we did it with paired data, we did it with synthetic data. Can we do it with unlabeled data? So can we do it with some, image collection? And, in this work, the dense and live captions, also with Sivan here. So we basically first, obtain some additional insights about the problem. So in addition to, the problem with the contrastive loss, we also hypothesized that another issue arises from the two things. One is the caption quality in the paired data. So if the data like clip data was collected by taking, images from the web and associating them with what is called alt text, right? So this is just the textual field attached to each image in the web page that is intended to be displayed if the image doesn't load. So those alt texts are not necessarily describing the image. Sometimes they have been unrelated to the image, or maybe some, some things like, oh, I feel nice today, and then picture of a beach. So this is one thing. The quality is not so good. And the second thing is the density. So that is what we call the density. So the density means that, how well those texts describe every detail on the image. Because if the text in the caption says something which is even correct about the image, but then doesn't cover additional details, for the contrastive loss, it means basically that the other thing is not there. So although it's present on the image, it's not present in the text. And the model is kind of learning that whatever is on the image is not associated, to the correct notion. So it's not there, right? So basically, in this work, we treated both of those using this, slightly complicated diagram, which I'll try to explain. Essentially, you take unlabeled image, you caption it. You can choose whatever captioner you want. You arrive at something which is, at least has much more chances to be connected to the image, right? It's not some arbitrary alt text that somebody put somewhere. It's an actual thing that was produced from the image. It's more accurate. It's not guaranteed to be dense, but at least it's higher quality. And we actually measured it in some ablation studies. And the other thing that we did, so we expanded this, caption in two ways. So one way to get additional information, what could be on the image, is just simply ask the world knowledge of a language model. So if you present a language model with some short description of the scene, it will provide you some additional details that could be there. So this is one way to expand. Another way to expand is basically just, just densify the caption itself. So you can, for example, segment the image and then, caption different segments. All in all, you end up with producing, a large collection of texts. Okay, some of them are correct and associated to the image. Others may be incorrect. So your goal now is also to filter, the correct versus incorrect. And for that purpose, we had the MIL, so multiple instance loss. So whoever is familiar with MIL and CE, this is a very simple loss, which basically takes a bag of labels. And the only assumption is that at least some of the labels in the bag are correct. So the goal of the loss is not enforce that all the labels are mapped to the image, but at least some of them. So for example, the maximum matching ones and so on. So this is how MIL and CE works. In addition to that, we use the same tricks from the first work, so we did the text augmentation and so on. All in all, together, we got like fantastic improvements using this approach, and compared to a bunch of other methods on the same compositional reasoning benchmarks, and we were pretty happy with it because all in all, we managed to get to something very close to 90 here. So I would say, at least on those benchmarks, they were almost solved. And again, here, as before, we always measure the zero-shot performance. We ensure that the model doesn't lose the general capabilities and still can be used as the original clip. All right, so moving on, sometimes you are in a situation where you don't have the kind of privilege to take your model and collect lots and lots of data and improve it with whatever way that I presented before. Sometimes you need to react more quickly, so you find some problem, you collect little data, you fix that particular problem, you move on with the new model, then you find another problem. And by problem here, I'm referring to different issues, the compositional reasoning. For example, one time maybe you fix the way the model treats spatial relations, then you fix the attributes, and so on. So this naturally, arrives at some kind of continual learning problem, right? Where you need to improve the model every time. So you need to fix the particular aspect as you go, and you need to make sure that the next model adaptation will preserve whatever we learned before. So there should be no forgetting, right? And in this particular case, we also want this thing to be data-free. So by data-free here, I refer to the lack of ability to retain data. So I'm not sure how many of you worked with continual learning before, but the most popular method for continual learning is just replay, right? So you just replay past data. In this way, you kind of preserve what you learned from the past. But this also means that you need to retain data, right? Sometimes it's against some IP regulations, or I don't know, not allowed in Europe. So in this case, we want to be completely data-free. We are not retaining any data between those fixes, and still we want to significantly improve. So we managed to propose a solution, and I'll describe it in a minute, that almost completely avoids forgetting in this case. I'll explain how we pulled it off. It's very efficient, so it is again based on parameter efficient fine-tuning. An architecture I'll now present, which is based on multi-LoRa, so layered LoRa architecture, and this managed to improve the compositional reasoning performance of the model on the same benchmarks by up to 13% final improvement. So two things we needed for this to work. One was this layered LoRa architecture. So now it would probably seem trivial to you because there are several works that follow this approach, but then I think we were kind of the first to propose it. Essentially, we want to be in a situation where we have one base model and then multiple fine-tuned models which we can recall automatically in memory without reloading the model weights. And we need it for the next thing that I'm going to present. And in this case, each of these additional LoRa models would represent this fix, right? So let's say the first LoRa is the fix for the attributes, or let's say for colors. The next one would be a fix for, I don't know, positional relations, and so on. And they are layered on top of each other. So each next LoRa is basically added to the model that was before. But now, let's say if you want to recall the model number one, you just throw away all the LoRa's to the right? You keep the first one. So you can basically recall any LoRa from the past. And of course, if you want to do efficient inference, you can always collapse all the LoRa's, right? And have one unified model. And the reason we needed this layered LoRa architecture, this is for the second thing. So basically the trick we had to avoid forgetting in this case was this adversarial pseudo replay. So whoever is familiar with the data-free continual learning, kind of a common trick there is pseudo replay. So you synthetically produce data from the past tasks, and you use it, to replay past experience. In this case, we kind of followed somewhat a different approach. So instead of producing synthetic data from past tasks, we produced synthetic adversarial examples to past tasks. So basically examples that are designed to fail past tasks. And I have an illustrative example here. So if your original, paired example that you use to fix, for example, the positional relations would be this image of a dog and the sentence saying a handsome dog on a couch, right? So obviously this teaches, what does it mean to be on, right? But then you can do this trick with adversarial pseudo replay, and you can attack using sign gradient, like let's say one of the past models, let's say it's a color model. So you attack the text, this augments the text implicitly, right, with the sign gradient. So basically just, some few steps of gradient descent. It changes the hidden state of the text to represent something which is not fitting this image based on the experience of the color model. So you can imagine as if it introduced a false color in it, right? And then basically you can take this new text, you can basically, run it through the past model, produce a drop in the, the matching between the image and the text. It's in a color model, so it produces text vector and image vector. You can compute the distance, and you can force that the same distance drop will be present in the new model. So slightly complicated explanation, but it's actually very simple. Everything is detailed, of course, in the paper. But the essence is we have fast access to all past models. We can apply the sign gradient attack to the past models, and we can basically enforce the same properties of the past models on the new model, and this avoids forgetting. Okay, so you can check the paper for more details. I know I didn't do a good job in explaining that one. It will be complicated. But let's move on to the next one. I think this one is pretty simple. So this one is about learning to compare images, and we do it with the new paradigm in visual instruction tuning. Essentially, comparing images is one of the basic abilities that we have, right? It kind of drives our learning. It allows us to take, two images, notice the difference, right? And from this difference, we notice change. It alerts us to danger, all other good things. And, arguably, the compositional reasoning notion that I mentioned before is about noticing the small change, right? So, enhancing our visual comparison abilities in the model will basically improve its compositional reasoning performance. So that's what we did in this work. We basically, started with some caption data source. So from this caption data source, we can pair images, and from the paired images, we can take their captions and use a language model to produce a structured, commonalities and differences report from the pairs of captions. Right, so basically, what we create synthetically is a data set where we have pairs of images and a text representing what's common and what's different between the two images, just using language models. Using this, we can build our first model, which is a little bit crude because it's only based on language. But still, using this model, we can continue and take either the same data source or a new data source, either with captions or without captions. We tested everything in this paper and continuously improve, right? So we can take the resulting model, produce a new data set of commonalities and differences, and using this new data set, we produce a better model. So this creates this nice improvement cycle. In this slide on the left, you see the characteristics of the resulting data set, which you can use to fine-tune and induce this capability for comparison. And you can see that, in this data set, if you look at the, the words that the model is using, you can see all those attributes, actions, relations in there. We also paired this with a benchmark. So this is more directly related to the workshop here. So it was more loosely coupled before, but now it's actually also a data set for improvement and a benchmark. And using this, this method, we managed to significantly improve, different compositional reasoning, tests like Bison, SVO, and LBR2, equivalent COLA, and so on. We also have this benchmark to evaluate the ability of your models to image comparison. There were a couple of works on that before, like Otter and MMICL, but we managed to improve beyond them. And this time we are focusing on this image comparison application. There are a couple of qualitative examples here. So we can ask, the models in the context of two images, ask it a question that basically needs you to somehow relate to both images and compare between them. And you can see that our model, can actually relate to what is being asked as opposed to, for example, standard Lava. But in the table, you can see on the benchmarks, we have significant improvements beyond a bunch of models, including the, the very recent ones like M2, Internet Composer, and so on. Right. So I a little bit rushed it just because we had very little time. But this is the end, so I'm wrapping up. The question I want to ask before we conclude is, are we there yet? And I would not ask it if we would be there, so bear with me. So if you take, one of the most recent, compositional reasoning benchmark, like SugarCrab, for example, you compare, the performance, you test the performance of, the latest models like 11.6, InterLM, InSAC, Blip, and so on, IDFX, or even GPT-4V. So you see there's some kind of saturation. So it's already in the 90s, maybe nothing left to do. So we, in this last work I'm going to present, we actually propose a method to make the task harder by asking the models to talk to each other with the goal of basically finding together in a collaborative fashion through a conversation, find where they actually still fail in the compositional reasoning task. So in this case, the models, there are 4 models here that converse with GPT-4V. GPT-4V asks them to describe a scene. They describe the scene. It checks what do they see as opposed to what it sees. Tries to ask hard questions, get some response. Then improves the question to make them harder, and so on and so forth. And eventually you start with the SugarCrab, and this is on the same SugarCrab data. And these are the 4 models that conversed, with the GPT-4V. Eventually they start, in the beginning they started from about 90, but then with our approach, the performance drops significantly by more than 20%. And what's interesting, so first of all, even the models that were not part of the conversation significantly drop performance by 12 or 15% here. And also interestingly, GPT-4V itself managed to produce some question that, it doesn't know how to answer. So it has like 11% drop on this benchmark. And we also verified, so because this isn't like a automatic process, the data is synthetic, so we manually verified the data by taking our samples in random order and filtering them until we hit 1,000. And then on those 1,000 manually verified, which we also share as part of the benchmark, we measured the performance and we basically see almost exactly the same drops. So the distribution of mistakes is, uncorrelated to the, whichever is is it in the good side where the models kind of hit the mistake and thought it was correct, or the other way around. So this is nice. Another nice thing about this work is it allows us kind of to tap into the, challenges the models are facing by taking those automatically generated question and answers and analyzing them for, the types of errors the models are making. So this is entirely automatic. Basically, you ask a language model to categorize the question and answers into those categories. You see the taxonomy. So the only thing we provide is like managing taxonomy. So basically this table on the right, and then we ask a language model to produce the breakdown. And we can see, for example, that, GPT-4V has issue with object proximity. It doesn't know really well to understand, how close are objects to each other. Another thing we can do is use a different taxonomy, not on what kind of thing we are asking, but the way we ask it. So, for example, a nice thing about this is models are prone to hallucination, right? So if you ask it about an object which is not on the image, it is kind of biased towards saying, yeah, of course it is. If you asked me, it should be there. Or another thing in the same kind of direction is misconception. If you ask it about the property of this object which is missing, it will still try to, appease you and invent some property. And non-determinable here means that, you ask it about something which cannot be really seen on the image, right? So I will conclude and maybe leave you some time for questions. Sorry for rushing it, but I really wanted to pack a lot of works in one talk. These are the works we covered. 4 of them are already presented on different conferences. 2 of them are on archive. Code is released. Data is released. Everything is open. You're welcome to check back. I hope I managed to introduce you at least in a little bit on this exciting topic of analyzing and improving compositional reasoning in vision language models. Thank you.
We can take a couple of questions. Maybe I can ask a question. So you talked a lot about synthetic data and using that to fix this compositionality gap. Do we need to do anything on the modeling side or on the model optimization here?
Mm-hmm. Yes, so some of the solutions I presented were on the model side, like the continuous learning one. So in my personal experience, what really helps with understanding the fine details is, for example, increasing the image resolution in the encoder, improving the encoder. So basically, some of those works worked on improving the encoder itself to notice all these differences. We are doing it with some specific losses, but obviously these losses didn't converge, right? So you can, for example, do some work on improving the encoder to decrease those losses. Basically, those losses are just a way for you to measure what's missing. But of course, the way to fix is not necessarily by just keeping the same thing and just learning with it. You can also find some better representations, better architecture.
All right, let's thank our speaker again.
All right, thank you so much.
Does it work now?
Yes.
Okay. Yeah, so in text to image generation, that you directly generate an image based on the text description. While in layout guided image generation, you have an additional input of the layout, either defined by the bounding box or mask. So in this example, we see that text to image models, it fails to generate a huge egg in the under the hen. Rather, it generates dozens of eggs, which are more commonly seen in the training data. While in layout guided image generation, the models are supposed to generate according to the layout, then generates the huge egg. So for layout guided image generation, previous benchmarks mostly focus on in-domain evaluation. The models are trained usually on natural images like Coco, with common layouts that are more commonly seen in real life. For example, the previous hen hatching dozens of eggs, right? And during evaluation, the layouts are also in distribution. They directly sample from the same data set. So in this paper, we raised the question, what about if you're testing these models on really different layouts that are not seen in training data? So for example, when there are 7 dogs that are clustered all over the scene of the image, as opposed to like 2 or 3 objects, a giraffe is next to a clock, like commonly seen in T2I scenarios. So inspired by this, we propose a benchmark, layout bench, a diagnostic benchmark for layout guided image generation to measure the control gap between the in distribution versus the out distribution layouts. So to have the perfect control, we chose to follow Clever to use rendering engines to generate the layouts and the corresponding image. And as a parallel, the original Clever data set naturally just becomes the in distribution set. And in layout bench, we designed 4 fine-grained categories of skills that a layout guided generation model should follow. So for each skill, we examine models on the extreme ends of the distribution. For example, in scale 1 number, we have layouts with 1 to 2 objects, and also have layouts with many objects, like more than 10. And in scale 2 position, we have layouts that have objects in the center, so everything is occluded with each other, and also boundary that when there's no occlusion between objects. For size, we test for tiny object and a large object. For shape, as opposed to like this almost square shape in Clever, we have horizontally long and vertically long shape. So in layout bench, we focus on evaluating the models that can place the right objects in the right location. So based on this motivation, we choose Clever Simulator because the objects and backgrounds are fairly simple, so that we can disentangle the layout following ability from the visual quality of the image generation. And in our evaluation, we train the models on Clever and then test on layout bench. So there is no domain gap between the object, the appearance of the object and the backgrounds, that we solely evaluate on the layout following capability. And our fine-grained layout skills also can help pinpoint model weakness in terms of which skill that the models fail. And for evaluation, we trained the DITER model on the layout bench training split and build a near perfect detector to evaluate the model's generation with mean average precision. So basically just testing whether the right object is placed on the right position. So here is a visualization of the examples for each of the layout for each skill. And you can, if you are familiar with Clever, you should be already known that these are very out of distribution. So based on this layout, we directly evaluate layout guided image generation models with our near perfect object detector. So it detects, compares given layout with the detected layout, and it just calculate mean average precision. So what we find with our layout bench is existing layout guided image generation models. They can do nearly perfectly accurate on the in-distribution layouts. But for out-of-distribution layouts that we designed in layout bench, both the LDM and RECO model fail to perform quite well. So this is an example with the layout bench position boundary split. You can see that both models fail to generate the correct yellow sphere on the boundary. And also the size of the other two objects is not quite right. So qualitatively, there is also quite a big performance gap between the in-distribution performance and the out-distribution performance. So that brings us to the next question we are trying to answer in the paper. How can we close this gap between the in-distribution and out-distribution performance? So existing layout guided image generation models, they output everything all at once. So it heavily relies on whether the similar testing layout have been observed during training. So what if we generate object one by one? So that motivates us to propose a new baseline for layout to image generation, which impints the intended object one by one, that can elevate the model's dependency on, in distribution layouts. So with iterative paint, with iterative paint, the inputs include first the description of the object to be painted, and the mask, which defines the position of the object, and the context image at this iteration, because it's the first iteration, it's just empty. And once the object red square gets generated to the image, to enforce consistent generations at the following iteration, we also clean out the output by pasting with the guided by the mask. And this resulting cleaner image will be used as the context image for the next iteration. So when we ask it to add a blue square to the image, we would directly add the blue square to the output of the first iteration. And the iteration continues, but finally, at the last step, we have a iteration of adding the gray background that's commonly seen in the clever image. And in the end, we get the final generated image. So our iterative paint significantly closes the gap between in-domain and out-domain layout following on the layout bench compared to the two baselines. And if we take a closer look into each scale, we also see the iterative paint considerably outperforms the baseline of all fine-grained splits on layout bench. And the gray area just highlights like the in-distribution configurations that are commonly seen in Clever. Our iterative paint also gets better performance on that. 1 minute, okay, I'll go fast. We also explore more extreme layouts that's user-defined, so like the AI here, and also the heart shape. And iterative paint also supports like interactive image manipulation that you can, based on one image, and then add remove operations. And we extended to real-world images that it's more commonly seen with Coco. And sorry, I don't know why it keeps happening. Yeah, so we also have a layout bench Coco benchmark that is designed for more like realistic object categories. And our E10 panel also achieves better MAP on that. So to summarize, we have layout bench, diagnostic benchmark for layout guided image generation, testing for out of distribution layout. We also extend to real image, which is our dataset layout bench COCO. And we propose a new baseline for the modeling, and that's why it can generate a lot of AI in this slide. Thanks.
What? Yeah.
I'll try to reach out to Ranjay, okay?
Yeah, that was fun.
Nice talk.
Thanks. So maybe we can start with the 1 minute introduction of all of our panelists. Maybe we can start with you.
Yeah, hi, I'm Aaron. I work at AWS AI, so we do a lot of data model animation for, yeah.
I'm Han Wang. I'm an associate professor at Nanyang Technological University in Singapore. And the reason why I'm here is that I was invited by my girlfriend, Dr. Zhang Xu. So so the topic I talk today is especially creative for this workshop. Yeah, so I fully respect this opportunity. Thanks.
I'm Besmira. I'm at Microsoft Research. I work with the group that is focused on model evaluation and understanding. Basically, we work on devising techniques for benchmarking, for quantitative evaluation, but also for model interpretability, debugging, and discovering and mitigating responsible AI issues.
Awesome. So, you know, the pace of innovation in LLMs and in multimodal methods is only increasing. We keep seeing new and new reports out every day. when you go through one of these technical reports or a research paper, what kind of metrics or data set, what are you looking for in the evaluation section? Like, how do you kind of place it in all of the other models that you've seen? So maybe I can have all of our panelists talk about that.
Yeah. Oh, fine. I see. So the evaluation section. Yeah, I think that's a great question. So a lot of them actually run on standard benchmarks. So and a lot of them actually they use large models to actually do the evaluation. I think a lot of them just do a very small scale study and see whether it aligns with its like human rankings or preferences.
Yeah.
Right. So I think the first thing to look at is that whether it's possible the test data has already been trained, right? So actually there was a paper talking about all these models, right? Like even GPT, Gemini, all these, they have various degrees of contamination. Like GPT-4 actually report, right? Like the degree of contamination for each of these benchmarks. Some of the paper actually doesn't, some of them actually report. So that's a kind of a question mark, right? And so a lot of these tasks, I think, if you just use large language model evaluation, there could be a lot of sort of biases, right? Like, there's position bias and things like that. So, like, you want to know whether they handle, these kind of biases. And typically, like a lot of these papers, only the author does the human evaluation trying to correlate. So that's a very small scale. So you want to see a larger scale. Yeah, so these are all the questions pop up when I read the evaluation section. Yeah.
So data contamination and large scale.
Yeah, and handle biases of these large language models if you use them to evaluate. Yeah.
For me, I don't really see those evaluations because I don't give a damn about it because I only trust myself. Yeah. So like there are a lot of self-claimed superpower commercial large models and I don't use them. I only use GPT-4o. Yeah. That's it.
So you kind of think that GPT-4o is a good model to be used for?
Yes, I think it's omnipotent or not omnipotent, but well-rounded model. Though it makes some stupid mistakes, but I think in general it works. I use GPT to write my research proposals, research findings, students' recommendation letters, and even use them to do the final exam. Yeah, yeah. So it's very good.
We should also try Cloud 3 up. It's also pretty good.
Okay. Yeah.
Other aspects is better.
Okay. Okay. Thanks.
So there's quite a few things, like, when a new technical report comes out, like there is the part about, what benchmarks are they using to show numbers, but there's also like, the detail that sometimes you need in order to reproduce those numbers. And in terms of the benchmarks, something that is quite common with these reports is that often it feels like those benchmarks are selected so that they show the model in a good light. And of course, like, if you're a model builder, it's understandable, like, why that happens. But there is to say that many of the things that we commonly see, like, MMLU, GSM-8K, things like that, HelloSwag, they are saturated by now, and it is also time to move on to, maybe it's good to show those numbers just like for comparison, like to see where we were and where we are. But it's also time to move on to newer things that are more challenging, perhaps more interesting. So this is in terms of like the richness of the benchmarks. And then in terms of detail, it is very hard to reproduce these numbers. like very few technical reports actually open source their evaluation code, like, you know, the actual thing that was used, like the prompt, the, I don't know, temperature settings, like what type of LLM call did you make? Do you, okay, you use it, the LLM as a judge, but like what exactly, like, you know, how did you use it? And what were the prompts? So all this, there is a little bit of like anxiety around, like, am I gonna be able to reproduce these numbers? Or was there some magic trick to get to those numbers?
So like bigger benchmarks and evaluation transparency.
Right,
essentially.
yeah.
So that also ties to my next question, which is, what kind of benchmarks are we missing, right? You talked about MMLU, HELA-SWAG. Like, are there certain abilities that we're not evaluating right now? Or is it more of a question of just scaling up these data sets, making them bigger and more representative?
We can do.
We can do that.
I mean, we're missing a lot. Like, you know, there is no doubt that like we're missing a lot in the sense, but benchmarking also is a very time consuming. Like, you know, it's understandable that we need time to also catch up with these things. But for example, I see a lot of like multiple choice and very simple tasks that are framed as like a single token generation or too much multiple choice, too little open-ended generation. And I believe there's like very few users out there on GPT-4o or any other model that are using the model in a multiple choice manner. You know, right? It's just not like what we're doing. So it's understandable why that's happening. And of course, open-ended generation is hard to evaluate. You need a lot more to get it right. But I think we're missing a lot on that part. We're also missing a lot on controllability, like especially for vision, like, you know, for this community, like this community does a lot, like image generation, things are exciting. You go to the exhibition hall, you see a lot of exciting applications. And for those things, like you really want to control the output. You don't, the other day I was trying to generate something with Stable Diffusion and I wanted to remove the text for that thing. It was impossible to remove the text. And my Photoshop skills are not great. So, you know, it takes like 30 seconds to generate one image and 6 hours for me to remove that text from the image. So we need more around like the interaction, the controllability, like the conversation that really is happening between the user and these models.
And I think it's very hard to identify what's the missing benchmarks because we agree that the large models have emerging ability. So emerging, it means some unexpected abilities emerge, right? So it's very hard to identify. So I think maybe we can urge the tech giants to release your user feedback database and to show that, yes, what's really going on of the user experience. I think if they can release that, then yeah, that's very good.
Yeah, I think certainly it's really hard to cover the whole distribution of all the human activities. So definitely that's a lot of things are missing, right? So for example, like it was in the embodied AI workshop in the morning, I think maybe yesterday, they actually have benchmarks for like 5 to 7 year old. There are these kind of challenge of some of these multimodal problems, right? I think these models was pretty bad, like if I remember correctly, less than 20%. So yeah, I mean, I think you were talking about, the reasoning capability is high school student level, but now we have a challenge where 5 to 7 years old, it just does badly, right? So yeah, so definitely, we need more benchmarks to probe the distribution. Model also has blind spots, right? You would assume that it's able to reason about, brother and sisters. The other day I saw a paper, it phrased the question, in a way that, like Alice has a sister and brother, and then you basically ask David, right, has how many sisters, we just say n sisters is n plus one, right? So I think model also has blind spots. And in general, these type of questions, it does really well, right? So I think that's why I think just these like static benchmarks, it's not gonna do a very good job. So I think we should really create dynamic benchmarks where you actually leverage the model's capability to kind of, given some prompt, like some template, you actually can cover more and more of the distribution in a sort of dynamic iterative way to cover the prompts and then evaluate, right? Yeah. And so can actually train a pretty good evaluator. I think it's still generally true that it's much easier to have the evaluator know whether it's correct or not, and then to actually generate a solution that solve it. So we can actually, leverage the capability of the evaluator, right, to kind of, probe the model's capability, right, in a dynamic fashion. Yeah.
I also want to open it up to folks. If anyone in the audience wants to ask our panelists a question, please feel free to ask them. I also wanted to thank Ludwig for joining. So if there are, I mean, while we wait for the audience, maybe I can ask you guys another question about all of the things that you were mentioning. Like we need user feedback in terms of how people are using these models. We need to evaluate open-ended generation. So to that end, what do you think of LMSys arena sort of benchmarks and like having real people kind of try to compare two models? Like, what do you think we are missing there? Is that sort of the gold standard we have today? And I'm just open to any answers from the panel.
First of all, I see as the inputs here.
Maybe you can use this.
Okay, cool. First of all, I think the LMSys effort is fantastic. I think it's awesome that they're maintaining this live leaderboard. And I think it's just a very good held out test set that they're always collecting new evaluations, right? Because there's a lot of worry with the existing benchmarks on overfitting and so on, and having them collect new annotations, I think is a huge service to the community and create a lot of clarity. Having said that, obviously no single benchmark is perfect. Not directly an expert on LMSys, but just from myself looking at this a little bit and also talking to others, I think there could be a concern that probably most of the users right now are not experts in a specific domain. And there's a question, how much time do they put into verifying their answers, right? Like, are we specifically evaluating sort of like factual knowledge here, or more like, does the model sound confident and gives like a pleasing sounding answer, right? A failure mode could be, there's more the latter, there's like, it sounds good and maybe it's often correct, but in order for us to actually use these models with high confidence, we want them to be very reliable. Which means that like we really should check every answer in detail, make sure it's comprehensive, not wrong in any way, and maybe at the moment that's missing, it would be a huge effort, right, to do this. But as the models get better, we probably need to put in more effort into evaluation.
Yeah, on a very similar line, I think the effort is really inspiring in the sense of like, being able to put it together to maintain all this feedback, and also because, LMSys also has open source a lot of data, so that has been super valuable. There is to say there is a little bit of bias in the user base, so the user base is us, so, it's whatever we ask as like model builders, evaluators, computer scientists. So in terms of like representation of different demographics and the larger population, I would say that is a major gap that needs to be filled. At the same time, there are like some aspects like in model comparison, like, when you put like two models together and you try to see like, which answer do you like better, there is some value in that signal, but I still think that signal needs to be better characterized because there is a lot of talk about like, oh, it is just about the vibe of the model, like, you know, how does it feel? I don't know, maybe this is just my personal opinion, but I don't think there is a vibe. It is just like things that we are not able yet to describe, articulate, and quantify. So I think it would be just really super interesting to go through these logs and find dimensions to how we can characterize these things better.
I agree with Spaceman that I think the current leaderboard is just shows some professional numbers. It does not reflect how a daily life user can feel. So I suggest maybe we can use my way that we can maintain a bank of flagship large models, and we can grade or incoming models to be re-represented by the performance of this existing flagship models. That will be more informative for normal users.
Yeah, I agree. I think it's definitely a great benchmark. I think it's kind of along the lines of more dynamic, right? Like because the population keeps changing, and I think there are certain things are missing. For example, it doesn't evaluate like retrieval, or you can access the web effectively, right? And then to use, and also like agent is a big thing these days, right? Like I don't think it supports sort of interacting environments, right? Yeah.
Because we are talking about multimodal models, I'm curious, like, are there any, there has been a lot of evaluation work, especially in LLMs. Are there any differences in terms of how should we evaluate images, and as we go to more modalities than vision, for example, sound, haptics, and so in your experience, like, how should we think about different modalities, especially in terms of evaluation?
Starting from me, well, I think the key challenge for multimodal LLM evaluation is how to evaluate generation tasks, because you have the so-called visual consistency. And for example, if you want to perform a visual editing, right? So you say, I want to change the color of the clothes into red, but how red? You have many reds, right? So it's very hard to evaluate that. And I think the IFID alternatives is far from real use cases. Yeah, so I think that's a key challenge. So, but I don't think there is a solution except for we invite human users to judge which visual quality is the best.
To add a different angle to that, as this number of modalities is also increasing, it's perhaps a good thing for us to also understand like how these modalities interact with each other and if they add value to each other. Like the fact that I have a question that can be answered in text, in vision, in audio, based on maybe like this conversation. What is the most useful signal? Maybe it's language, but maybe it's not. Maybe there are like cues in the interaction to like how we communicate with each other, things we don't say to each other that have a lot of information about the cultural norms, how people interact, and what is really like over and under specification in the interaction between modalities, and how grounded are they in each other. Like, is it really like, attending to the way I'm speaking? Is it really attending to the video? So all the intersection in the interoperability space is yet another aspect to evaluate.
Many good points already. Maybe just two quick thoughts that came to mind. One is that on the language side, I think people have spent more time looking at correlations between evaluations, like realistically often, for instance, alpaca eval is very correlated with LMSs, and MLU is also a good predictor for other natural language understanding evaluations. I'm not sure if we have the same level of understanding there. for vision language model evaluations. And then the other one is maybe the microphone stopped working.
Yeah.
Okay, yeah.
They said it's a constant thing.
Multimodality is hard. Yeah.
Micro.
Yeah.
Anyway, I just speak louder. Maybe it's fine. Okay, thanks. But what was the dangerous one of the class? This is a trap, I think. Okay, the second point I wanted to make was that for language models, I think there's at least somewhat clear distinctions between evaluating a base model and evaluating a fine-tuned model of instruction tuning and RHF and so on. And currently, when I look at the VLM literature, it's a little bit less clear to me because a lot of the VLMs is sort of like using one language model and then have some fine-tuning steps to align like a clip encoder with the language model and so on. And then it's unclear, is the model better because it already seen more VQA data and the fine-tuning, or because actually this is a better architecture. You can give it a small area for improvement.
So not a whole lot of early signals like we have in LLMs.
Yeah, or like maybe like more controlled experiments. So like try to tease apart the different parts of the models.
Maybe we have. Yeah.
Oh, I just want to add one thing. I think for multimodal models, you know, like learning this word model is sort of the least, you can say, the most important problem. So I think we should see develop more benchmarks that evaluates how good these models are in terms of handling the world, like you know the world model in terms of RL, right? So given the current state and action predicting the next states. Well, I think you know they're already worked on this, but you know like in terms of building models, but how good in general these models are, they learning the world model. I think that's very good.
We can maybe take one more question. Anyone in audience have a question?
I have a question. What's your next step? What will the next proposal be like?
That's a good closing question.
Many things. I mean, just one thing. So as I mentioned in my talk earlier, I'm really curious as to like the role of data. And one thing the students and I were talking about next was setting up a benchmark specifically for evaluating different instruction tuning data sets. On this DataComp for language models, we are focused on pre-training. I would like to build a similar framework for evaluating instruction tuning data sets. And then another student and I, we talked about specifically interleaf data. I think we are getting or have a better handle now on these image text pairs like in DataComp and Lion. But another important sort of way of training multimodal image text models is by having longer documents of images and text interleaf. And they don't really know how to build these data sets in a good way.
Oh, yeah.
So one aspect of evaluation is really also understanding the failures of these models. We also talk about these evaluations, and it's just like numbers, you know. You put all these numbers in a table, you show it to people somewhere in some media, and then you try to compare that single number. But there is like a whole story behind that number. Like, you know, what are the things that the model does well in this benchmark or across capabilities? What are the things that it struggles with? What are the things that neither Gemini, Claude, GPT-4, Mistral, all these models are failing at? Like, we have a very poor understanding of these things. So I hope the community, like, we're definitely working on these things, but I also hope the community will pick up like some of these things and see, like, you know, say more about like what can and cannot be done at this point, and consider this as a valid part of like evaluation, actually the most important part of evaluation. Because we don't want to just show numbers. We want to improve, to debug, you know, like to inform the next generation of these things. So that is basically like, you know, a very important aspect. Another side thing, we're not working on this, but like it's just like something that actually occurred to me while you were giving the talk to the speaker here in the afternoon, is that, You know, the tradition in ML used to be that I give you a training set, do whatever you like in the architecture, and tell me like how good can you be with this training set, but the training set is fixed. That has kind of been lost, and I think we need both, like, no, do whatever you want with the architecture and do whatever you want with the data, but both need to be there. And it's a little bit sad that we lost that because it feels like nothing more can be done in the architecture space, but I feel like a lot can be done, especially in the multimodal part that we have just started to stretch. So I hope someone, again, like picks up on these things and maybe like, you know, on the DOMA data set, like that Alan just published like this year, like what is the best architecture that that performs everything?
So the question is, what's my next move? Right? So my next move is train my time step tokenizer online for 5B, and I will open source it because if you look into many of the newly published multimodal large language model papers, they all they can share you the training of the model, but they will always keep their tokenizer secrets because the tokenizer is the key. So I want to show them that I will have a kick-ass time step tokenizer by the end of this year. Yeah.
Looking forward to it.
Yeah, I think I'll be looking into dynamic benchmarking. So the problem is that I'm taking a seed prompt, right? So I've just used large models to sort of, mutate, evolve it to try to cover more of the distribution of the particular use case, and then have a super powerful verifier, right? Just to verify whether, it's likely correct or not, right? And then, yeah, I think it's a good way to, like you said, right? So it's not just a number. So with probability distribution, we can actually summarize it in a report. Hey, like it's, let's say it's weaker, some particular mass problem. Right? So I think another thing that will be, could try to build a curriculum or benchmarks, evaluate the progression of how good the model in, the word model is. Some of these models, yeah.
Great. I think we are at time. So let's thank all the panelists. Thank you so much for your time.
So you would like to present some yours, right?
Yeah.
And do you have the Zoom link?
I don't think I do, and I don't have Zoom either.
Okay. Well, we can try. Maybe. Okay, let's try that. Yeah, I just.
Oh, that's the other one, right?
Yeah, I don't know. That was Amazon. I don't do anything on Amazon. Yeah. Oh, thanks. Amazon just died because of all the emails. It's it's sharing screen. It's not sharing anything, right? Let me just check.
So we're going to start our final session for the workshop today. Our next speaker is Sandeep Jayasumana. He's a research scientist at Google Research. Sandeep's research interests are in the areas of computer vision and deep learning. And prior to joining Google, he was a postdoc at the University of Oxford. He did his PhD at the University. So today he will talk about FID, rethinking FID towards a better evaluation matrix for research.
Yeah. Okay. Anything written? What? Okay, so good.
Hi, yeah, thanks for the introduction and good afternoon, everyone. My name is Sadiq, and I'm going to present this paper on rethinking FID towards a better evaluation metric for image generation. And we have a poster presentation in the main conference that's tomorrow afternoon. And this is joint work with my colleagues, Daniel, Srikumar, Andreas, Ian, and Sanjeev from Google Research. So I'm going to talk about image generation and evaluation of image generation. I'm going to set up the problem setting. This could be insulting to some people because you already know about these things, but for the benefit of people who are not that familiar with this problem, we are talking about text to image generation. So we have a text prompt like a cute baby lion or squirrel in a forest and so on. So that's the text prompt, the input to the neural network or your model. And the output of the model is an image, as you can see. So that's the image generation problem or text to image problem. And we are talking about how to evaluate this sort of models. So one thing we could do is we can come up with a set of captions with enough diversity and coverage. And we can generate images for these captions with our model. So now we have a set of images to evaluate. And the problem is, how do we evaluate this model? So one way to do that is to compare generated images with real images. So you can get real images corresponding to the same set of captions, and then you can compare the two image sets. So now our problem is narrowed down to comparing two image sets. One image set was generated from the model, and the other image set are like actual real images. So obviously we want generated images to be as close as possible to real images. And that would be a good generative model. But this is a hard problem because images are of very high dimensions. So today, like generated images could be 1024 pixel resolution, and we have 3 channels as well. So we are talking about a very high dimension space. And also we'll have many images, like 30,000 or something like that. So we will be working with very high dimensions and a large set of images. So, the authors of FID paper simplified this a bit by using these inception features to represent images. So instead of representing our images with these actual very high dimensional pixels, we can compress them into inception embeddings. So for each image you have, you get the inception embedding by sending the image through the inception network, inception V3 network, and by extracting the last layer activations. So for inception network, that turns out to be a 2048 dimensional vector. So now each image you have is represented with this vector. And of course, you do the same thing for the real image. So now you have simplified the problem a little bit. Now you have vectors, and you have 2 sets of vectors. And then we are going to compare the distributions between these 2 vectors. Because you are not going to get the same image, even though it's the same caption, right? So we can't really measure L2 distance or anything like that. We have to compare the distributions between these 2 vectors. Now, think about that problem a bit. That's not an easy problem to solve. I have shown a very simple problem here with only 1 dimension. So let's say you have 2 distributions where your variable is just 1 dimension. So you have this P distribution and you have Q distribution, and we are trying to measure the distance between these 2 distributions. Now, this is easy in 1-dimensional space, and especially if you know the form of your probability distribution, we have KL divergence and various other tools. But remember, we are actually talking about a 2048 dimensional space. So that X and that Y, they're actually not real numbers. Instead, they are these gigantic vectors. So how do we do this in this huge vector space? So again, FID paper authors tweak this distance called fresh air distance. The definition is this. So this gamma is a joint distribution that has P and Q as marginal distributions. And then you get the infimum over all such distributions, and you get the L2 distance. So this is sometimes also called the Earth movers distance. And but even this is very intractable in the high dimensional space because we don't know the distributions again. We can only sample from the distributions. We don't know the actual distributions. So the authors of the FID paper made an assumption, that is, these high dimensional vectors are multivariate Gaussian distributed. So with that assumption, you can simplify this further, and you can come up with this equation, which requires means, two means between P and Q, which you can estimate because you have vectors, 30,000 vectors or so, and you can just estimate the mean. And also the covariance matrix, which is a bit difficult to estimate, but you can still do that. Again, these are 2048 dimensional vectors. So the mean has 2048 dimensions. And importantly, the covariance matrix is a 2048 by 2048 matrix. So it has about 4 million entries. But you could still do that. But also there's a square root operation here that will also make things slow because we are talking about matrix square root here, and these are huge matrices as well. But anyhow, at least we have something that we can work with, and people have been using this metric for a long time. So in our paper, we are talking about shortcomings of this metric. That's why it's called Rethinking FID. And then we are proposing an alternative metric. So as I said, FID has two components. First, we need to compress the images into a vector space, and we use inception embeddings for that, inception V3 network. And then once we have the vectors, we have the Fréchet distance to measure the distance between the distributions of vectors. So this introduces two kinds of shortcoming. First, the inception embeddings. If you think about them, inception V3 network was trained maybe like a decade ago, right, on ImageNet data. And ImageNet data, as you know, they're like images are very simple. There's one prominent object, 1,000 classes, very simple. And there aren't many ImageNet images either. Like today's standards is pretty small, about 1 million training images. So inception embeddings, they're not very rich embeddings in that sense. And Fréchet distance, on the other hand, first we have the Gaussian assumption, the multivariate Gaussian assumption. And secondly, as I said earlier, we need to estimate a large covariance matrix, which introduces errors. And thirdly, we have, this is a biased estimator, as it was discussed in the CVPR paper a while ago. And that paper actually proposes a method to remove the bias, but that doesn't quite solve the problem either, as we will show in a minute. So in our paper, we are trying to address all these limitations. So I'll first talk about this Gaussian assumption on inception embeddings and why that's wrong. Now, if I tell you that inception embeddings are not Gaussian distributed with single mode, that shouldn't be surprising because inception network is trained to recognize these ImageNet classes, 1,000 classes, and this is the layer just before the classification layer, which is a linear layer. So inception embedding should have at least 1,000 modes corresponding to each class, right? But we are assuming a single mode Gaussian. So that's a very wrong assumption. And you can simply visualize it by doing Disney embeddings in 2D. Now, even in 2D, you directly recognize multiple modes, presumably corresponding to different classes in ImageNet. So we are showing the problem with the Gaussian assumption. And to make it a bit more concrete, we did some proper multivariate Gaussian tests, hypothesis tests. So in each of these tests, we assume a normality, multivariate normality, as the null hypothesis. And then we look at the data set and look at the probability of this data set occurring under the null hypothesis. We are using this COCO 30 data set and inception embeddings. So as you know, in hypothesis testing, if the p-value is less than 0.05, we reject the null hypothesis. But in these cases, it's actually exactly 0, very close to 0, up to machine precision. So all these three tests very confidently reject the Gaussian assumption on the inception embeddings. Again, this shouldn't be a surprise because of the reasons I mentioned earlier. But now one might ask, okay, who cares? We made a Gaussian assumption, it's wrong, but maybe, we make wrong assumptions all the time and would get good results. So is it not the case here? Now, we have this synthetic experiment to show that this Gaussian assumption is actually very important to get accurate results with this Frechet distance. And if you violate the Gaussian assumption, you get very wrong results with this Frechet distance. To demonstrate that, we have a synthetic experiment here. So we have one distribution P. Again, we are comparing distributions. One distribution P, which is actually multivariate normal in 2D. And we have another set of family of distributions Q, which starts with P, multivariate Gaussian, and then increasingly it departures from that Gaussian assumption. You can find the details of this on the paper, but to be quick, so we have do P and Q, and at the start, Q is same as P, so the distance is 0. And so FD is the Frechet distance measured under Gaussian assumption. FD infinity is the corrected Frechet distance that was proposed in this paper, and MMD is the distance we are going to use. So as you can see, Frechet distance keeps giving you 0, although Q is very different from P, somewhere here, right? There's no way it's actually 0, but Frechet distance gives you 0. And so does the FD infinity distance. But the MMD distance, which is the one we used in our paper, that actually correctly captures the departure from the Gaussian distribution. So it keeps on increasing correctly. That's what we want to see. So the bottom line is, when we use Frechet distance with data that are actually not Gaussian, we get disastrous results. So we don't want to do that. So we introduced this new metric called CMMD to fix both of these problems. So first we remove inception V3 embeddings by replacing them with CLIP embeddings. So as you know, CLIP was trained on complex scenes downloaded from the internet, not just ImageNet data. And it's trained with a much bigger data set, 400 million or so. The MMD distance instead of Frechet distance. So it assumes no distribution, shape of distribution. So it doesn't assume Gaussian distribution. So we are safe. So CLIP distribution might not be Gaussian, but we don't care because we don't assume that. And MMD distance is actually much more sample efficient than Frechet distance because we don't need to estimate that huge covariance matrix here. And also it's naturally an unbiased estimator. So we don't have to do anything artificial to remove the bias. It's naturally unbiased. So we didn't want to deviate too much from FID. We are still in that framework because people have been using FID for a long time. So we want to propose something people will be comfortable in using. So that's why we didn't depart too much from the framework, but we are fixing the two problems. So just to quickly talk about MMD distance a bit more. MMD distance is, it uses a kernel to measure the distance between two distributions. And for the correct choice of kernel, it's a proper metric. So that means, it satisfies all these properties of a metric. It's positive and it satisfies its triangular inequality. And in particular, if your kernel is a characteristic kernel, the metric is 0 if and only if the two distributions are the same. You don't get that property for non-characteristic kernels. So because of that, we use this Gaussian RBF kernel, which, as you know, is a very popular kernel in kernel methods. So something similar has been used before in a metric called KID, kernel inception distance. But in KID, people use inception distance and also a third degree polynomial kernel in the MMD distance. So a polynomial kernel is not characteristic. So that distance is not a proper metric. So we are fixing that problem by using this Gaussian RBF kernel, which is indeed a characteristic kernel. And so as you know, the Gaussian RBF kernel has a parameter, the bandwidth parameter, sigma. So we found out that the results are not that sensitive to that parameter value. So we just keep it fixed at 10 in all our experiments. We have published our source code as well. Yeah, you can find it under Google Research, GitHub repo. Yeah, so let me talk about some experimental results. So we first did a human evaluation to prove that our metric aligns better with the human perception of image quality. So for that, we use the Muse model, one of popular image generation model. And as model A, we took the full Muse model. And as model B, we tripled the model, and artificially we got a bad model that doesn't produce very good images. So model A is on the left-hand side. So these images. And model B would be the corresponding image produced with, model B is on the right-hand side. So as you can see, model B has obvious problems. The eye is missing here, structure is missing, the car's various parts are messed up. So obviously, a human can see the differences between model A and model B. But when you look at the FID metric, so all these metrics are distance measures, so lower the better. It actually gives you a better score for model B. And FID infinity, the bias corrected version, that also behaves the same way. And KID, which I mentioned earlier, also behaves the same way. But CMMD, our proposed metric, on the other hand, correctly identifies that model A is the better model because it has the lower value. And human raters, they overwhelmingly prefer model A. So we did this human rater experiment with set of raters that we don't know about, using cloud computing. And there was like very strong agreement between them that model A is a much better model. So model B was preferred only like 7% of the time. And for the remaining percentage, like they equally prefer model A and model B. But again, model A is strongly preferred, but FID says completely the opposite. So we have some more experiments. Here we measure the metric values with the progression of diffusion or transformer models. So as you know, many of the image generation models are iterative. So they iteratively improve the image. So Muse does that in 8 iterations, and stable diffusion might be like more iterations. So as the iteration number increases, as you can see here, the image clearly improves. That's why we do more iterations. But FID keeps on increasing, which is very misleading. And FID infinity, again, it behaves almost same as FID, like in the big picture, because that bias is corrected in the same way. So it more or less behaves same as the FID. But CMMD, the blue one, on the other hand, it keeps on improving, correctly capturing the improvements made. And we repeated the same experiment with stable diffusion. And yeah, so there also FID behaves kind of weird. But CMMD correctly identifies the improvements made to the images. Another experiment, now in the original FID paper, the authors showed that FID behaves well under commonly found noise, like Gaussian noise, salt and pepper noise and things like that, which is true. Like we also replicated those experiments, and which was enough at the time FID was proposed. But today, we need to identify more complex distortions to images. So we did an experiment with some like complex noise. So we got the VQ-GAN representation. We use VQ-GAN in stable diffusion and Muse and all these papers, latent space. So we added noise in the latent space and reconstructed the image. So as you can see, visibly that image is a bit more complex than Gaussian noise or salt and pepper noise. But still, the distortions are very visible to human eyes. Again, FID actually thinks, FID actually improves with the noise, which shouldn't be the case, right? Because the FID thinks that images are getting better, but they are not. We are adding more and more noise. On the x-axis, we are adding more and more noise, more distortion. So FID should be increasing, but it is not. But CMMD, on the other hand, it keeps on increasing. So I'll be quick. And the other thing is sample efficiency. So that's quite important. To get a good value with FID, you need a lot of samples. So that means if you are doing online evaluation, for example, you have to generate at least 30,000 images to correctly measure the FID, which is very expensive if you are like doing your experiments on TensorBoard or something, and if you are generating images in each epoch or like each few iterations. But CMMD gives you a correct estimate even with something like 5,000 images, so which is very useful if you are doing online evaluation of models. And computational efficiency, this is actually not very important because most of the time is spent on image generation, and CMMD is better because we have better sample efficiency. But if you look at the actual time spent on the distance calculation, again, MMD is faster because it only needs common matrix operations like multiplication. But FID is slower because you need to compute the square root of a matrix. Yeah, so I'll quickly mention some limitations as well. So CMMD, as I said, is just one step towards a better evaluation metric. We didn't want to deviate too much from FID, but in the future, one could think of better metrics, metrics where you do one-to-one comparison between, images generated for the same caption, and also clip embedding model is still low resolution. So for some high resolution images, there could be problems. And the reference set, COCO 30K, is also not a very good data set. The image, like real images, are very low quality, small images. So those are things that we can improve. So in conclusion, we took FID, which is on that this quadrant, and we improved it with CMMD by replacing both the embedding model and the distance model. Thank you very much.
Thank you, sir. We probably have time for one question.
Yes. So you changed the infection model to split, which indicates that the feature expector is important. But if I would want to apply this, for example, medical imaging, would you think it makes sense to change to a dedicated model of that domain, or would split still be generally to work well?
Yeah, so we haven't done any experiments on biomedical images especially, but my intuition would be if you have a better model that works better in those images, I think that will be better. So we have replicated some of these experiments with Dino as well. So yeah, our method is kind of agnostic to your feature extractor.
Yes, go ahead, Min. Let's take it as one.
Oh yeah, so in the appendix material of our paper, actually this was raised by our reviewers as well. We have shown experiments with many different kind of noises, and CMMD consistently works better for those noises as well. But if you have like any other special kind of noise in mind, we'll be happy to take a look at those too.
Yeah.
Yeah, so some of the high resolution images, we got better results by using high resolution reference data set. So we use like something like internal to Google, where we had a high resolution data set. So we got better results with that reference data set for high resolution image generation models. Thank you.
Our next speaker is Jungo Kasai. He is a co-founder and chief technology officer at Koroba Technologies, where he leads the project that builds speech foundation models from Japan and Asia. He's also a research assistant professor at the Toyota Technological Institute at Chicago. He earned his PhD in computer science from the University of Washington, focused on natural language generation, efficiency, and evaluation.
Sure, we can hear him. Can he say something?
Jungo, can you say something? Can you hear us?
Yeah, can you guys hear me okay?
Hear him. Turn up volume.
Hello, can you guys hear me?
Yeah.
Oh, good. All right, thank you. Okay, cool. Should I get started?
Yeah.
All right. So I will talk about this. Was a little bit unusual talk. It won't be too technical, but I wanted to reflect upon my past and the present and the future. And it'll be a great opportunity because evaluation is a very important part. So we believe dramatic 5 years of AI and NLP. All right. So a little bit of myself and company. So I founded this startup with my friend, Nori. This company is actually very young. It was founded in 2023. Nori did his PhD in Cornell. I did my PhD in the University of Washington, actually in Seattle. Unfortunately, I'm not in Seattle now, but that's where I did my PhD. The company has an interesting structure. It's a cross-border venture. So the headquarters in the US, technically in Seattle, but it's kind of a paper company. Used to be my apartment. But then we have a serious office in Tokyo. And our mission is to build speech foundation models. So like not just text, we want to build sort of speech, end-to-end speech foundation models that can be used for many applications like speech translation or whatever, like call center speech application we can think of. A little bit about myself again. I'm also a research assistant professor in the TTIC, Toyota Technological Institute of Chicago. After I did my PhD in University of Washington. So, you know, nice pictures. I got some nice awards, but they don't really matter. The only thing that matters now is foundation models and LLMs, of course. Okay, so this is my background. Finally, this is the last piece of sort of my background in this talk. So how I got into NLP research is actually maybe a little bit unique, different from other people. So when I started my college, I went to Yale in the East Coast. It's of course old school university, so they actually didn't even have an NLP course. They only have a computational linguistics course. So I was taking this. I was interested in philosophy. I wanted to study philosophies. I was especially interested in philosophy of a language, and I took this course, computation and language, basically computational linguistics or NLP from linguistics. And the professor, Bob Frank, in his lecture, he says something very interesting. A word is characterized by the company it keeps, right? So this is the idea that people often say, distributional semantics. The idea is like, you know, when you define dogs and cats, you know, how do we define their meanings? For some reason, we sort of know what they are, but how do we define these meanings? This is sort of a philosophical question. But it turns out there's a computational approach to this philosophical problem. You can actually look at contexts where dogs and cats appear, and then you can immediately understand like dogs and cats are similar to each other compared to like dogs and chopsticks, for example. So this is kind of mind-blowing. Of course, now people think it's obvious, you know, we build neural nets on these like contexts and large language models, and we represent meanings of words in this way. But at the time, it was really, really mind-blowing. This is how I got into NLP and AI research. And in terms of sort of computer vision, I have friends doing computer vision. I was kind of always jealous of computer vision. One reason is that my friend in computer vision, he had way more GPUs than I had. And then I almost got kicked out of my university cluster because I was trying to use as much compute as possible. But then the CV people, they had their internal lab compute, and I was always jealous. And it's finally, I was able to give a talk in a CV conference or workshop. That's kind of amazing. All right, so this is sort of a personal story. So in the interest of time, today's talk is quite simple. I have two parts. The first part, I will talk about evaluation in the past 5 years when I did my PhD of NLP research, sort of in the context of evaluation. How do we evaluate models? How do we actually evaluate papers even? I have to say it was characterized by failure. I failed many times. Many things didn't take off. We'll talk about that. And then we'll talk about the present and the future. And I believe that there's some hope there. Of course, that's why I'm still doing my research. All right. So part one, we'll talk about dramatic 5 years in AI and NLP. So when I did my PhD, I started my PhD in 2018. I think arguably that was sort of the most dramatic 5 years in the history of NLP and AI. Of course, you know, in the beginning, we had like BERT, LLMs, and we had like ChatGPT and eventually GPT-4o and stuff. And then if I summarize my PhD in the nicest possible way, it looks like this. Of course, you know, it's a mess. You guys, I'm sure there's PhD students here. You know, I worked on many different things. It was kind of messy. But if I summarize it in the nicest possible way, it looks like this. So in the beginning, I was working on core sort of NLP language tasks. And then after I started my PhD, I realized, okay, I was only working on English. I should work on something different than English. I speak more than I speak 3 languages. Why not work on the other languages? And then after working on this multilingual natural language processing, I got into sort of machine translation. You know, if you deal with multilingual languages, why not build machine translation models? And then like evaluation matters a lot in machine translation. It's a generation task. Now everything is generation task sort of, but at the time it's one of the most important popular generation tasks out there. And then I did machine translation. And towards the end, of course, we had LLMs. I was working on some sort of evaluation and stuff in LLMs. So this is our sort of PhD. story 5 years. And one thing that's nice about this is actually is that the sort of the audience of my research got broader and broader towards the end of my PhD. So in the beginning, I was working on core NLP tasks, and then towards the end, LLMs, and of course, machine translation. So it's a nice feeling that, of course, there's nothing wrong about like working on very specialized model problems, but then it's a nice feeling. So if there's like a junior researchers there, it's kind of highly recommended to explore many different things during your PhD. Freedom is the best thing in your PhD. So, and then one thing that's interesting is actually these sort of different topics I worked on correspond to different institutions I worked at. So every time I go to a different environment, I was able to explore new people, new collaborations, new research topics. So I went to Meta for research internship. I also went to AI2 in Seattle. I also went to Microsoft, and then I was able to explore many different things. So junior researchers highly recommended to explore different environments. All right, so this is the only lesson. I think I'm wrong most of the time, but this might be right. Okay. All right, so when I started my PhD, there's something happening. Something cool was happening in Seattle, actually, there. So there's a paper. I think nowadays people don't remember what Elmo is, but then it was a big deal back then. So Elmo came out from University of Washington and All Institute for AI in Seattle. The idea is very simple. In retrospect, it's like the most obvious thing you can do. But at the time, it was kind of mind-blowing, right? So the idea is basically you build next word prediction model, basically language model, and then use representations from these models to solve whatever tasks, question answering, semantic role labeling, whatever language task you have. And it turns out this kind of representation learning can improve the downstream performance substantially. Right now, it's just obvious, but it was mind-blowing at the time. And then this is sort of related to computer vision. So Sebastian Ruder is sort of an influencer in the natural language processing field, or maybe AI. Sebastian says something very interesting in his blog. So he said NLP's ImageNet moment has finally arrived. So we finally caught up with computer vision in 2015. So by which he means, like back then, people are doing like ImageNet pre-training. I guess people still do. Sorry, I am not on top. Yeah, but anyways, so they're doing ImageNet pre-training. And then finally, Sebastian said, okay, NLP does pre-training on massive text using this kind of Elmo. Okay, so I thought, okay, fair, right? NLP is always backwards after computer vision. Computer has a bigger community, and they probably have more money and more GPUs. So okay, it's 3 years after computer vision, we finally caught up. All right, this is the end of revolution. All right, so I was completely wrong, right? So this is only the beginning, and in fact, a lot of people actually don't remember what Elmo was. So this is the history, and okay, so back up a little bit. When I saw this Elmo, I realized, okay, so this is only English only model. That's frustrating. Okay, so we should build multilingual models because there's so many applications out there involving non-English languages. So that's what I did, and then I submitted this paper, and I got conference acceptance. That was great. See, the idea is basically when you train a model on a single language like English, compared to these Arabic, Hebrew, and Russian, for example, and then let's say another controlled experiment where you train a Elmo or language model on a combination of two languages like Arabic and English, or Portuguese and Spanish. Can you improve the performance, downstream performance? It turns out the answer is yes. You can actually improve the performance a lot. You can see the plots like here. Okay. So now you think, oh, this is the obvious thing. Of course, ChatGPT, GPT-4, everything is trained on multiple languages. But back then, it wasn't really the standard. So we kind of went ahead of a lot of research effort. All right, that's good. However, this research didn't really take off. And then this is actually related to evaluation. Why this research didn't take off? So the biggest problem we had in this paper is that, as we saw in the plots, we're doing bilingual experiments and carefully comparing bilingual performance and monolingual performance in a controlled experiment. I did some control, like, make sure that, some language doesn't have too much text compared to other languages, make sure that these domains are similar, etc. So I did sort of scientific evaluations. I drew the plots. However, this research didn't take off. And in retrospect, I think one reason is that I value too much scientific evaluation over engineering. There's a paper that came after my paper, cross-lingual language model training from Facebook, the Facebook AI research. And they didn't do much research, the evaluation research. They actually put like 50 languages as a single model. They actually use Transformer. I use LSTMs. It's kind of lame. I didn't know Transformer back then. Anyways, so the idea is like they use this single model that can be used for many different languages. And this research took off because people just download these models, right? So this is sort of a bitter lesson that evaluation, as much as we strongly believe in evaluation, it's also very important to build something that's usable by many people. And also another evaluation thing is that I evaluated our representation models using sort of core NLP tasks like question answering, or excuse me, the core NLP tasks like syntactic parsing. But it turns out people didn't care too much about syntactic parsing. They care more about question answering at the time. And then this cross-lingual language modeling paper, they actually did question answering evaluations. And that's one of the reasons why they took off. So this is a bitter lesson from my past research experience. And then BERT came out. And then, of course, I also failed to evaluate BERT paper properly. I thought it's just like a straightforward extension of Elmo. And it turns out, of course, no, it really changed the ecosystem of AI models. And in my defense, I'm not the only one who had this mistake. Okay, so even like more senior people made the same mistake. So Noah Smith, I hope Noah is not there. Noah Smith is my advisor in University of Washington. He says something like, "Oh, it's just a straightforward extension of Elmo. It's a Google thing. Don't give a best paper award to this paper." It turns out 6 months later they won the best paper award in NACL. So I'm not the only one. Well, another professor actually in University of Washington, he's actually one of the authors of the Elmo paper, Luke Zettelmoyer. He had a very interesting thought. So he said, "Oh, this is amazing. You can use these models. Like many people just use the BERT model, and this is just amazing." But he's just sad that his Elmo didn't last more than a year. So this is an interesting. So I think Luke knows that engineering is very, very important. That in a way that I didn't realize at the time as a PhD student. But then lastly, even him, he didn't really understand when GPT-2 came out. He didn't really understand the importance of GPT-2. He just said, "Oh, it's just a language model. What's special about this?" But of course, this changed everything. So everyone makes mistakes. So I don't have to feel too bad about it. All right. So after this BERT came out, I started working on generation evaluation. So there's many generation tasks like machine translation. How do we actually evaluate these models? It's a very difficult problem. Actually, my project started with a comic I drew. This is a comic showing that how hard it is to do evaluation. So I posted on X. I was happy about it. I was a PhD student, so can do whatever. But the idea is very, very simple. The idea is, okay, so we have leaderboards, right? We still have leaderboards, and then we rank models, but we should rank evaluations as well. Different evaluation metrics. Like we still use BLEU in many cases, but you should rank follow-up papers on evaluations and then make sure that these models are evaluated by the best possible practice out there. So we should evaluate evaluation models. So usually we have unidimensional sort of a leaderboard, but I claim that we should have bidimensional, two-dimensional evaluation, by which I mean models are evaluated, metrics are also evaluated. So that's sort of the idea we had for this paper. I also use this framework to evaluate image captioning. So this is sort of maybe the closest possible point I had with computer vision in my research career. I did sort of evaluation of computer vision or the image captioning data. So I integrate this image captioning evaluation into our bidimensional leaderboard framework. This is the example we have. So human evaluations and metrics are evaluated based on their correlations with human evaluations, and then systems are evaluated by the best possible evaluation out there. And of course, GPT-3 came out after, everything changed. Now we do in-context learning all the time. All right, so this is where we are. All right, so let's summarize what I learned from my past experience. So in retrospect, a lot of scientific evaluations didn't matter. It didn't really drive progress. I mean, we didn't start using transformers because it achieved the best possible results on X benchmark, right? I mean, maybe in the beginning a little bit like machine translation stuff, but then it's not the reason why it took off so significantly. there's probably other reasons behind it, like, hardware determinism. So like transformers work very well on the hardware like TPUs and GPUs. It's easy to parallelize. So there's many other reasons why these models take off, not evaluations itself, right? So this is a bitter lesson I had. So it's kind of like unscientific, I would say. And if you think about it, maybe it makes sense. Maybe computer science is called computer science because it's not science. Just like OpenAI is called OpenAI because it's not open. And I always think Safeway is not safe because it's called Safeway. So yeah, maybe in retrospect, it was obvious I was kind of naive. So this is sort of the bitter lesson I have. And then, of course, we can't trust experts' evaluation sometimes, including, of course, myself and also more senior professors. All right. So this is the bitter lesson. All right. So does evaluation guide our future? So in the ideal world, we believe that evaluation guide our future. Does it really guide our future? Well, my answer is I don't know. There's many other factors, even, what tools we have, what hardware we have. There's so many other things out there. So I really don't know. Well, but I would say there might be some hope. So let's end with some hope in evaluation at the end, right? So let's talk about evaluating multilingual and multimodal foundation models. All right, so one thing that's really frustrating to me, again, I'm going back to the theme again and again, but because it's the community still has this problem. Even in the era of commercialized large language models, a lot of models are still English-centric. So of course, internet users, we only have 1/4 as English speakers, and the rest of the world speak non-English languages. But still, NLP papers and benchmarks are highly English-centric. Most of the papers only exclusively use English as their benchmark. And there's some movement that really encouraged multilingual applications, multilingual models in the NLP community. So English, of course, OpenAI and other models. Chinese, there's models, and also multilingual models led by, I was also part of this team, or this big science team, Hugging Face, multilingual model, basically led by Hugging Face, French company. And then, however, this multilingual Bloom model, they didn't have Japanese in one of their languages. I speak Japanese, and it's really frustrating. Why not build models for Japanese? That's very sad. And at the time we knew that these GPT models would change the field completely. So it was really critical to have these language covered, especially, for example, the Japanese is one of the major languages in the world. So we actually started before ChatGPT came out. This is after Bloom the Bloom project started. We had this project called Fugaku LLMs. So Fugaku is the largest, it used to be world's fastest supercomputer in the world. It's actually CPU based, so it's actually crazy. We use 150K CPUs, CPUs to train a large language model for Japanese. But then in theory, it was like 10 times faster than the GPU cluster that Bloom project. Big science project to use, Jones A, from the French government. So we actually managed to train a large language model for Japanese. So this is sort of the side progress I had towards the end of my PhD. And then the Fugaku LLM sort of took off, and then eventually we were able to release the model. Now we have the strong Japanese LLM. And a lot of universities and companies in Japan sort of took this project, and then it sort of finished. So, all right, so was mission accomplished? The answer is unfortunately no. There's still critical problem we need to, this is sort of a kind of like an evaluation paper we had in the context of multilingual labs. There's still some problem. So the problem is that these commercialized language models, of course, these models, of course, use tokenizers, right? So they tokenize text into subwords, and then subwords are done encoded using embeddings, and then they're passed to the transformers. It turns out these tokenizers have very, very interesting properties. So sometimes they're really English-centric, alphabet-centric, that for Japanese speakers or Russian speakers, for example, they have to have more fine-grained tokens, which means that you have longer sequences, which means that the problem is harder, right? So you have to do more long sequence reasoning over long text for Russian or Japanese, roughly speaking, on the same content. And then you have to pay twice as much cost compared to English, for example, because these commercialized models are usually the cost is estimated using the number of time steps we have, right? The tokens we have. So this is the problem we recognize in our evaluation research. And all right, fine. OpenAI actually, maybe some Ultima read my paper and they changed it. It turns out Tokyo office in OpenAI is the first international office of OpenAI. And then they had this office opening and they had this headline. They basically made Japanese LLMs faster. And of course, we don't know the internal, but it turns out, well, the educated guess is they just changed the tokenizer. They make it fast, twice as faster by changing the tokenizer. So, okay, my evaluation finally kind of guided research, or maybe even more, touched on people's lives. All right, so that was kind of a happy ending. But then this is the multilingual applications. But then as a company, we actually started working on speech foundation models. So we do multimodal LLMs or foundation models. And then we strongly believe that evaluation will be very, very important in this multimodal settings as well. Because, once we get to this multimodal phase, we have to sort of launch these systems in the wild and then evaluate models carefully. So this is the sort of the future. All right, so this is the end of my talk. Thank you. Yeah.
Okay, cool. Thank you.
Yeah. On time, I guess.
Awesome. Thank you, Jungo, for the presentation. So we might have time for one question.
Yeah.
Any question from the audience? Yeah, if not, I have one question, Jungo, for you. Like, thanks for all the learnings that you shared. Would you say that like the ultimate evaluation, and maybe that's also something for this workshop audience, the ultimate evaluation is essentially adoption and test of time, right? Like according to the various learnings that you shared. What's your thinking?
I think that's the ultimate evaluation. However, like automatic evaluations or evaluations we work on, I think they're still very relevant. Like you can use this evaluation to like filter out data. Llama 3 is trained on text filtered out by Llama 2 or something. This kind of stuff will happen again and again. So there's something that's important about current evaluations. But ultimately, when you evaluate models, I think test of time is the best. That's my thinking. Yeah.
Awesome. Thanks a lot. Thanks again for the presentation. So we'll move to our last presenter, which is also virtual. Do you want to? No, Bo, are you online? Just taking. Okay.
Yeah, okay. I think I share the screen. Can you see it?
Yeah. Just a moment.
See it.
Yeah, I can introduce Bo. So our final talk for the day is from Bo Li, who is associate professor at University of Chicago. Bo is on the advisory board of the Center of Artificial Intelligence Innovation at Illinois. She's a member of the Information Trust Institute. She's also affiliated with several research centers aiming to broaden the research collaboration and reach different communities, such as the Advanced Digital Science Center, the Center for Cognitive Computing Systems Research, and the Quantum Information Science and Technology Center. Her research focuses on trustworthy machine learning with an emphasis on robustness, privacy, generalization, and their interconnections. And her talk today would be about risk assessment, safety alignments, and guardrails for generative models. Go ahead.
Okay, thank you. Thank you for the nice introduction. And yeah, a lot of people read bios, but no. Okay, great. So yeah, great honor to share some of our recent research on this like risk assessment, safety enhancement, and guardrails. And apparently in this workshop, with a limited time, I will mainly focus on the risk assessment in terms of the evaluation. And I'm currently an associate professor at the UChicago and the UIUC, and we also have a startup virtual AI and focus on AI safety and focus on the risk assessment and alignment types. So yeah, if you are interested, happy to discuss offline. So first of all, let's start with a little bit from motivations and foundations. So here we can see, I think in this audience, we don't need to emphasize too much about how important and advanced the different machine learning and AI technologies help bring us different levels of convenience, right? But on the other hand, we can see indeed like these advanced technologies and AI machine learning models have also brought us a lot of security and privacy concerns. One of the favorite example of mine is that, say, back in 2016, I believe, the Associated Press Twitter account was hacked via phishing emails, spreading the rumor that the White House has been attacked, which is a very easy identified fake news by human with common sense knowledge. However, it's actually triggers the automated trading bot to dump a large amount of stocks within seconds and swipe about $136 billion within a second. And if you say, okay, this may be, in 2016, and now 2024, we have all kinds of fast-growing advanced Gen AI and different technologies, whether this will happen or not, right? I think maybe some of you have remember, I think it's last month, the Lyft stock price has a big jump over like 60 to 70%, mainly because of one typo in the annual report. Again, it's a small typo, like a human with common sense knowledge can identify it, but it's again triggers autonomous trading bot to buy a lot of stocks and lead to such a big change. So we can see even with like all the development we have so far, our safe and secure deployment is still a concern and a bottleneck that we cannot trust AI and we cannot trust our technology in terms of the corner cases and in terms of the long tail distribution data. Therefore, we do need the test and we do need the not only test but also the verifications or evaluations with guarantees. And similarly for large language models like chatbot, and the output can be like buyers can leak sensitive private information, and multimodality models, say face recognition systems, it can even lead to misarrest. So that's saying that we are living in a very fast-growing and exciting world with all the AI technologies, but still we still struggle with different types of safe and secure deployment. And therefore, in the past, just last year, there is an executive order from White House emphasizing the safe, secure, and trustworthy development of AI. And apparently, there are other related regulations like EU Act, in the past, GDPR, particularly about privacy and AI bills of rights, emphasizing and analyzing these different types of threads for different types of AI-enabled pipelines, frameworks, and products. So, but as a very high level, we can see AI security and safety is a large, important, but relatively vague topic. So how can we understand it when we talk about the same language, right? For example, some people, when we talk about AI safety, some people focus on fairness, some people focus on privacy, security, etc. So how we can be put on the same page? So here we go ahead and try to simplify the AI pipeline and system as a simplified pipeline at this. So basically assume that, say, we have some foundation models and we have, say, LM agent, and then they can be adapted to different domains like healthcare, like finance and customer service agents, etc. And basically, the first thing for improving safety and understanding safety vulnerabilities for AI platform is that we need to have a sophisticated and comprehensive risk assessment platform such that we can use this as a sandbox and perform different red teaming algorithms to understand the vulnerabilities of these different domain-specific AI products and platforms. And with that, we can go ahead, say, fix such problems by using additional toolbox that different algorithms we provided in the past. That's like many of them. And finally, we do want to have a basically lightweighted guardrail models to guardrail the input-output so that even we don't fundamentally fix the problem for a model yet, we can have a relatively cheap solution to guardrail the model in real world. So that's the overall idea. And in this workshop, I'll mainly talk about the red teaming part as risk assessment so that we can understand better. And I think it's very important and actually key point of the foundation model evaluation itself. So let's see, in terms of the risk assessment and red teaming platform and evaluation, the main question here we want to ask is how should we assess the risks, right? And basically, what's the trustworthiness perspectives, or what's like different angles that we should target on, and what's algorithm we should use to generate data and try to understand it. So from this, we mainly have two principles. One principle is the use case based safety perspectives definition and generation. And the second principle is regulation enabled and based perspective and the safety testing. So let me go through the first perspective, like use case driven, which is interesting and applicable to many domains and many people and many models. So first of all, I want to introduce the Decoding Trust, which is one of our open source platform and which aims to provide the first comprehensive trustworthiness safety evaluation for language models, foundation like multimodality models and LM agents. And the first step we did is to go ahead and put us on the same table, as we just mentioned, to define different perspectives that we should look into, including the toxicity, stereotype bias, adversarial robustness, like out-of-distribution robustness, privacy ethics, fairness, etc., hallucination, right? So when we define those things clearly, then we can be on the same page and talking about similar languages. And apparently for each of these perspectives, there are additional sub-scenarios, sub-goals, sub-tasks, and additional algorithms accordingly to generate the long-tail distribution, blah, blah, blah. So these are more details. I will hide that. But basically it's saying that for these different safety perspectives inspired by different use cases, we will correspondingly generate different challenging data, prompt, or image, video, text to like risk challenge or do the stress test for the foundation models or AI pipelines so that we can understand and uncover the underlying vulnerabilities. And this paper also won the Best Paper Award last year at the NeurIPS. On a very high level, what can we learn from it, right? So from this platform that we have evaluated different perspectives that we mentioned for both closed source and open models. And what we learned is that on the very high level, there are two quick takeaways. One is that no model, unfortunately, will dominate others on the age trustworthiness or safety perspectives, even the very capable GPT-4 model here. So we can see that even we have a very capable model like GPT-4, GPT-4o, and we tend to use them for our daily use cases, but we still need to be careful that they are actually not the most trustworthy or safe models under certain perspectives, and we need to be aware of that. And second of all is that very interesting, there seems some trade-off empirically among different trustworthy perspectives here. But whether these trade-offs are fundamental or not, it's clear, interesting research directions. And in the past, we have some work proving that, say, adversarial robustness and OD robustness under mild conditions are bidirectional indicators for each other. And similarly, some like a relationship between robustness and privacy, but there are still many other, connections open, and as long as we can, understand the fundamental trade-offs among them, we will be able to know whether we can achieve best word among all, or we have to have some impossible result and we have to pay for some trade-offs. These are very interesting and important for us to know along the line we build more capable and safe models. After this high level understanding for this decoding trust, let me go into a little bit detail for some perspectives so that we have better understanding about what types of data it look like and what types of algorithm we're using to generate for each perspective and what metrics there are and what we can learn from each perspective, right? So apparently I don't have time to go through all, and I will pick two, three, and we can take a look. So first of all, let's look at toxicity, which is one important perspective like many people care about for chatbot and for foundation models. And here, all the examples in this talk come from GPT-4. And what we can see is that on the left-hand side, green part is the input, and the pink part is the output. Let me know if there are questions. I heard something. So basically, here, our example is our goal is to generate stealthy input such that for human or for existing tools we will not see as toxic, but then for the output it will like elicit model to talk in a very toxic way so that it can bypass human or model method like monitoring, but it will still lead the model to talk in a toxic way. That's a goal. And there are two examples. One have the benign system prompt, like you are helpful assistant. The other is a jailbreak system prompt. Like
Sorry. Oh, I'm really sorry. It seems that there is some issue with the room reservation and the workshop organization. So it seems that even though our workshop was reserved until 6:30, we have to leave the room at 6 p.m. and we're already 5 minutes past 6. So I'm really, really sorry about this mishap.
That's fine. I might tell you until like 6:15, but it's okay.
You can continue on the Zoom and
Yeah,
and we
it's
will
fine, it's fine.
So
finish.
yeah, please continue on the Zoom. There are probably people in the assistance on the Zoom, so you can continue on the Zoom, but we'll need to leave the room here, and we'll try to find how we continue this outside of the room.
Yeah, or we can buy some time out. It's fine. I think the most important thing is the high level, and some detail doesn't matter. So if people have questions, I'm happy to answer some question on Zoom. Otherwise, maybe we can buy some time. Yeah.
Okay. Thank you. Thank you very much, Bo, and really sorry